pause a live stream? Are you serious? Where are we taking this?
There, because it's 7 people, so I'm just afraid that we should not use 1 year. I don't know,
Okay, fine.
because the other person will sit there. 2 is 7. So we might just want to put the camera there.
Yeah, sure. Ah, Jesus. Shocking.
So, first question. Do I say good morning?
No, it's 1 o'clock. Jesus
do I say?
Christ, woman. Good afternoon.
Good afternoon, it's too late, no?
It's 1 o'clock.
Afternoon is
Afternoon.
Okay,
Afternoon.
good afternoon. Okay.
Especially here in Denmark, we are very precise.
Yeah. Plus, I mean, it's going to be dark in a few
Dude, this
hours,
is so...
All right. I'm going to the bathroom now, okay? Okay.
And I guess
This is so tall,
But
man.
I need to pack all my stuff.
Is this just going to be for the camera? Because then we can move it all the way here and I can have a wider... Yeah.
Guys, do you have the link?
Huh? No, you just have to search YouTube for Mafalda PhD Defense.
Oh, please.
It's currently live, you know that, right? So everything we're saying...
No, really?
Yeah, yeah.
Okay. Link, please.
No, there's no link. You just have to search.
No, send me the link.
There's no link. I can't. It's on my phone. Tiago's going to have to send you the link.
I can try to find it on my computer.
Just search Mafalda PhD
Search on YouTube.
It's very easy. It's simple. We kill that man.
You can search Mafalda PhD Defense YouTube and then she'll find it.
Yeah, exactly. It's very simple. Oh, I know.
Is it okay there?
Yeah, it's fine. I mean, the angle's a bit weird, but we should be able to see everything. Although it's also going to be a bit awkward for, because I think someone at least should sit.
But if you're there in the corner, you'll just stand there as the cameraman.
Yeah, I guess so. All right, yeah, you're right. It's just going to be fine.
There's a little bit of lag.
Yeah, no, there will be some.
There's like a 2-second lag. I just entered the link and the first thing I saw was your ass. Yeah.
Sign of a good defense, man.
Yeah, but I can always log in and see if the video is still
Yeah, exactly. So maybe you should be watching it on screen.
Oh no,
3 hours.
Need to look at stuff.
Are you here tomorrow, Rowan?
Only for the morning presentation, and then I have to bounce very quickly after that. And why am I saying this on the live stream when we have a viewer? Oh, you're the viewer?
Yes, I'm the viewer.
Good.
I'm most likely the viewer, yeah.
I apologize to all listening. Later on, when this is on demand, we will try and edit it down to just the defense. Right now, it's just going to have some random.
That's good. Then you're here for your birthday.
Part of my birthday. I'm traveling on my birthday, but it's
Are you turning 25 or 30?
25 or 30, those are the options.
Yeah. Well, no, one of those two because there's special things that happen.
No, I'm not turning. I'm an intermediate. I'm at 26.
Yeah. That's good. 25 I would have to like coat you in cinnamon.
Oh, right.
30 I would have to coat you in pepper.
I
So.
recall. Weird Danish. I will make sure not to be in Denmark on any of those hallmark birthdays.
Yeah. I mean, for yourself, I would say the 25 one is the worst one because
Cinnamon?
getting coated in cinnamon.
Cinnamon could kill you.
Also because it reacts with your sweat and forms cinnamon acid.
Oh,
that
cinnamon
starts dissolving your skin, and
That's perfect.
yeah, you can get third-degree burns all over your body. It's wonderful.
Well, it was like earlier today, Tiago and I went to go and fetch something from the furnace. They forgot the forceps, so we were just like, well, the furnace was still at like 400 degrees, so both of us like scorched our knuckles a bit.
going to some of these defenses worries me because it's like some people have so much stuff to talk about, and I'm like, I'm not there. I don't have that much stuff I've done. And then I go to some of the others and I'm like, oh, that person did like one thing.
Yeah.
I'll be fine.
Yeah.
Okay?
She's just gone to the bathroom.
Bathroom.
Okay. Important. Hello.
Right.
Ik wil nog een café. Can we? Come querida. Olá. Mano. Esse telefone?
Yeah, I did.
You already sent the link. I have the link.
Onde é que eu falo? No fundo estou.
You can run it on your phone while you're giving the presentations and watch
2 second delay.
2 seconds delay of yourself giving the presentations. Oh, I'm sorry, I didn't smile.
Olha, tá assim, gravando. Tá em live streaming.
Até ali, mais. Sim, tens acelerado, ou pelo menos faltaram alguns falhantes.
Where is my thesis? Where is my thesis?
It was over there.
Ah, it's right here. You disse? Oh my God, leave the door closed for now.
I will. I'm gonna go and get a fancy coffee. Do you want anything?
No, thank you. I'm too nervous to have a coffee. Sim, só um segundo. Não preciso disto aqui. Depois tem que ter a cabeça.
Não, ainda não. A parte final do projeto sempre vai estar em
Ai. Isto é a pior parte.
À espera para começar.
Sim! Qual é que é o plano de visão aqui? Oh meu Deus, vem mesmo. Era não assim, agora sim, porque já lá estás. Ali não está a vir em live streaming. Só está cada um assim. É isto. Também vai cheio, Tiago, vamos lá festa do
Eu vou fazer o departamento, não vou tentar ficar muito claro.
Então podes vir, é seguir, é azul. É tipo, anda, agora é o meu ano. Tu não tens isso uma coisa. À esquerda. À esquerda é o eu venho procurar, nada.
That's about.
can't believe you're here today. How did you do it? You knew it from when did you know that you had your...
When you told me that your defense was on the 5th of December.
Oh my god.
Ok.
Thank you! Obrigada! Hi Murray! Olá Leonor! Beijinhos!
You've already got 1 like, Mafalda. We're gonna make millions. Smash like and subscribe, guys.
For the seminar, but I get your point. The other way that people
Yeah, I mean, it's just because some people might just be like, no, they'll build them up because they know that they'll be
but that's correct.
Sim, é a minha terceira caminho. Olá, pai. Já mandei. Já mandei.
Claro que sim. Agora deixa-me verificar se está envoltado.
Eu já disse ao Homer e agora já mandei.
Phone isn't charging.
Isn't?
No, that's bad.
It is charging or
It's
it
not
is not
charging.
charging?
It's not charging. Is the power on then?
It's this one.
Hmm.
Why is that not working?
Is the you're wrong.
Yeah, maybe as a...
The red dot on the
Here.
there's like a red dot there.
This.
What is
It's
that?
not, it's not illuminated.
Eu escondi as canetas todas. Escondi as canetas todas para não mandar no meu quadro.
Carolina, I know you can hear me, all right? It's very creepy that you're starting to send me messages now.
Nada, não vou tirar
I can try the other one.
Rápido, super rápido.
Yeah, just change it. Let's see. Because the laptop is charging, right?
Yeah, don't touch this one.
What about now?
Is it charging?
Change the plug as well.
Nope.
Nope.
Interesting.
Mine is...
I too am a budding engineer, so if I can't figure this out.
Wait 1 second. See, I found the solution.
Yeah. Now it has to be.
Otherwise, it's your phone.
Oh, Tiago's solution was terrible.
Does it work? Do you think it's your charger?
No, it worked yesterday.
It should be.
Ah, there we go. Starting now. It's just a very finicky angle.
Was this the connection?
Okay, the audience is asking if we can remove the chair on the bottom right of the corner,
Bottom right?
because
It's the audience.
they're picky audiences.
Can we share?
Yeah, I already shared.
No, but we can share that.
Yeah, please don't touch your phone.
Share it to everyone, guys.
Only on my...
Let's get this to 1 million viewers.
Set off. It's not, sorry. It's already charging, right?
Yeah, it should
We
be
have
charging.
12 people online.
12 people and 4 likes. Come on, some of you aren't pulling your weight.
Hey, close. Online.
Ben,
No, it's charging.
okay.
Because yesterday I was at
This is like the
Yeah, it was just the angle. It's because it's been like kind of cold. But anyway, I'm gonna leave it for now.
Lá acima.
Oh, now we only have 11 viewers.
Não, fui eu 2,9.
Se calhar
Se calhar 2,7. Eu cheguei lá assim, meu, calma. Não, aqui.
Podes tentar se quiseres.
Então, como é que está?
Estou nervosa.
Ai, calma. Onde é que você está?
Olha, a minha mãe está aqui. A minha mãe está aqui.
Não, mas só consegue dois. Sentar. Tem que dar um papel ao John. Estou bem aqui? Eu trouxe uma perguntinha ou duas para o Rei.
Dude, when you shave your mustache, it be so awkward to look at you.
Estava a dizer, Rafael, estava a dizer a Alex, com uma ela é mais
O bem para o mal.
I went earlier because you were setting Say, just go to the camera, tell them nice, just cell phone What is this?
Estamos bem, estamos aqui bem. A Ivone vai para aí. Não, a Ivone não vai. Não, és tu.
Well, that's the second one.
Did you and your sister coordinate your outfits?
Yeah, we did. No, not.
It's like in case you want to dig gumbo. You're just like, I'm tapping you in.
Yeah, the necklace.
My dad buys himself me and my brother a single. Yeah, she will reach.
The son, my sister's brother, was always like, we have to all watch it because there's as well as in the when does it start like bring up the views?
Oh no, YouTube how many hours can I add? So 10,000 hours when we film these
What if you only do like the
Close in here. Okay.
Twitter,
Now the real oxidase expert.
Good afternoon, ladies and gentlemen. My name is Inês Kuning from DTU Chemical and Biochemical Engineering, and it is my pleasure to chair this public PhD defense. I would like to welcome the examiners, Principal Scientist Shane Grosser from Merck, USA, Professor Andreas Sebastian Gomarius from Georgia Institute of Technology, USA, and Associate Professor Manuel Pinelo Jimenez from DTU Chemical Engineering, who is the chairman of the assessment committee. Also, welcome to the key person of this afternoon, Mafalda PhD. And finally, welcome to all of you in the audience. The event this afternoon marks the conclusion of Mafalda's PhD study at DTU. She has studied at the Department of Chemical and Biochemical Engineering under the guidance of Professor John Woodley as main supervisor and Associate Professor Ulrich Grüner as co-supervisor. In a short while, Mafalda will give a lecture on understanding the scale down of oxygen-dependent biocatalysis. This is also the title of the thesis. After the lecture, the examiners and the supervisors are entitled to ask questions to the candidate. If anybody else in the audience wants to ask questions concerning the scientific work, please let me know during the break. According to the rules, the time allocated to the lecture is 45 minutes, and the entire event may last no longer than 3 hours maximum. After the lecture, we will have a short break. Now, it is my pleasure to give the floor to the candidate. Please, Mafalda.
Thank you. And so, good afternoon, everyone. Thank you very much for coming. And today I'm here to talk about my PhD thesis. And so my thesis is called Understanding Scale Down of Oxygen-Dependent Biocatalysis. So in a very simple way, I would like to say that scale down is an activity where we try to replicate the conditions in the laboratory that we find in large-scale bioreactors. But before talking about scale down, I would like to introduce biocatalysis. So biocatalysis can be defined in many different ways. But for the purpose of my work, I've defined it as the use of enzymes as catalysts for chemical synthesis. And the enzymes are these molecules that are proteins that do catalyze chemical reactions in all living organisms. These enzymes have very interesting conditions, interesting characteristics, such as being renewable. Also, they can operate under mild reaction conditions, and they have very high selectivity towards chemical reactions. So, but in reality, how are enzymes interesting to apply in industry? So, these features of enzymes, when used as biocatalysts, can actually offer high product qualities due to the high selectivity that they offer. And they also reduce chemical waste, and they do create safer processes. All of these will contribute to the development of more sustainable processes. But the one thing that really differentiates enzymes from chemical catalysts is the fact that they are tunable. And this was shown by Frances Arnold, who won the Nobel Prize this year on chemistry for the directed evolution of enzymes. And so this ability to tune a catalyst means that we can actually adapt it to meet industrial process requirements. And this task of modifying an enzyme and alter its properties is done by protein engineering. The possibility to modify the enzymes actually offers great orders of magnitudes of improvements in the process when compared to traditional process engineering approaches, where we were used to adapt the reactor, the process conditions, to match a certain chemical catalyst. But even though protein engineering is such a wonderful tool to develop more sustainable biocatalytic processes, there is a need to identify the limitations of a reaction system in order to direct this research. So process engineers also have the role to analyze the processes, identify these limitations, and set targets for changes in these enzymes. So there are many classes of enzymes, many types of enzymes. And some have been successfully implemented in industry, but predominantly in pharmaceutical industry. As an example, a very well-known case is the production of sitagliptin. It's an active principle of Januvia, the medicine as an anti-diabetic drug, and this is produced by Merck, and it has even won the Presidential Chemistry Award for a greener reaction conditions process. Another example is the production of the active principle of Lipitor, this medicine that some of you may be familiar with, that is also done using enzymes. But, however, not all enzymes have been applied in industry nowadays. And this is due to the complexity of the reactions that they do catalyze. And so, as an example, one of the most complex reactions to perform are oxidation reactions. These are very important in organic chemistry, and they are extremely hard to perform selectively. So enzymes with the features that I presented before could actually perform these reactions in a much more selective way. So these enzymes, oxidases, and other enzymes that do perform oxidation reactions have been gaining a lot of interest in the chemical industry nowadays, and my thesis will mostly focus on that. So let's have a closer look into bioxidation reactions. Bioxidations are applied in a variety of fields, as the synthesis of fragrance and fragrances, pharmaceutical intermediates, And the way I was saying, enzymes, when they are used as biocatalysts, they normally, the ones that catalyze oxidation reactions, are part of a class called oxidoreductases. Within this class, there are other two subclasses of enzymes called oxidases and oxygenases that are very interesting because they do use molecular oxygen as an oxidant. They also generate hydrogen peroxide or water, and they do require cofactors. But like I mentioned before, they have been rarely implemented due to its challenges and the complexity of these reactions. So I mentioned that molecular oxygen is a very interesting feature of these enzymes. However, it has some challenges to overcome. And so even though molecular oxygen is really is a good oxidant, innocuous, it's a low price, it has to be supplied. And if we look at a large-scale bioreactor, we have to supply it by sparging a gas phase in a continuous way. So we will have a gas and liquid interface. And then we need to steer in order to ensure sufficient oxygen transfer in the medium. And these conditions bring challenges to the enzymes and can create process limitations. So one of the limitations that can come is related to the rate of reaction. The reaction rate may not be fast enough. And why is that? So molecular oxygen has a very poor solubility in aqueous media where biocatalytic reactions take place. And so this characteristic creates a slow transfer from the gas to the liquid phase, and also the low concentration in the medium can actually compromise the efficiency of the enzyme. The second challenge that I would like to talk today, it's about the stability of the enzymes towards the presence of the gas-liquid interface. And the presence of this interface can have an effect on the oxidation of the amino acids and can also alter the structure of an enzyme and make it not be active anymore. So, in order to move bioxidation reactions towards industrial implementation, I consider that we do need to identify the major process limitations on these systems. Then we need to understand what is the underlying cause. So we will be able to propose improvement strategies for a research that will be more focused. In order to do that, so the question for my thesis came, so how can I study bioxidation reactions in the laboratory at an early stage of the process development? So that's where my thesis takes place. And so I would claim as the goals of my thesis were to investigate the influence of molecular oxygen on enzymes under these industrial relevant conditions that I mentioned before, but I will go into more detail later. And therefore developed a scaled-down approach specifically for biocatalytic oxidation processes with a major goal to acquire fundamental understanding on the kinetics and stability of oxygen-dependent enzymes. And finally, all this knowledge gained should be incorporated in the process design task. So my thesis has two major focus areas. One is on the kinetics of oxygen-dependent enzymes, and the other is on stability. These two areas are extremely important in the design of the bioprocess, of the biocatalytic process, because they do determine the costs of this process. The kinetic of an enzyme will have an influence on the productivity, on the product concentration that we'll get in the end, and also on the amount of enzyme that we put into a bioreactor, and that will have a cost. The stability is the same. It will have an impact on the biocatalyst field, so how much enzyme do we need to put into a process in order to make it work at the industrial targets that are desired. So, right from now on, I will focus on the stability part of my thesis due to the time that I do have. And So I will explain the work that I've developed under this field. In order to investigate the stability of oxygen-dependent enzymes, my major goal was to investigate the effect of gas-liquid interfaces on the stability of these biocatalysts, and under these so-called operational industrial process conditions. For that, I've chosen to use an oxidase, an NADPH oxidase, that I will call from now on NOx, that is here. And this enzyme uses molecular oxygen to convert these cofactors, NADPH to NADP+. And these cofactors are extremely important to be recycled when coupled with enzymes like alcohol dehydrogenases, which are very interesting because they can oxidize alcohols to ketones. But one of the problems of this reaction right here is the fact that they do require these cofactors and they are quite expensive. So they do need to be recycled, and NOxes are enzymes that could do this job and actually be very favorable. And they are important because they do favorable the thermodynamics of this reaction. That's one of the reasons, and also because of the presence of molecular oxygen as an oxidant compared to other chemical oxidants. So from now on, I've used NADPH oxidases, and with the goal to investigate the influence of the gas-liquid interface on enzyme stability, I've developed a setup to study these three factors: the sparging of air, the oxygen concentration, and steering. So for that, this small-scale bioreactor with 2 Rushton turbines was designed, and additionally to this typical setup, I've added an optical probe that we can see right here. So it's an endoscope attached to a high-speed camera with a backlight source in order to see the bubbles inside the liquid. And this tool was developed in order to measure the interfacial area. So in this way, I was able to incubate my enzymes in conditions that I would assume that could be very similar to large-scale bioreactors. Because we could steer, we would have a lot of gas inside. And I could actually measure that interfacial area and quantify it. So that's what I've done. I've decided some conditions. I've incubated my enzyme in that laboratory scale bioreactor. And from that incubation, I've sampled in 2 different ways. One of them, I've sampled to measure the kinetic stability of my enzyme, so to measure how fast my enzyme deactivates over time. And the second sampling method was to measure this gas-liquid interfacial area by the videos. So let's take a closer look to the first part. So the first thing we observed here was that, so I measured the residual activity, so I measured the activity of my enzyme before being exposed to these factors and over time, and then the ratio of that, it's called the residual activity. So how much activity has my enzyme lost over time when exposed to these conditions that I've applied. And so the first result that was observed was that with the increase of power input, which is how fast the reactor is steered, how much energy we put to steer the reactor, the enzyme stability decreased. So then, in order to quantify this deactivation, I've used the first order deactivation model in order to measure the deactivation rate constant, so we could compare the results in a more quantitative way. So this observation was done, and then let's take a look at the samples from the reactor. So what I've done was to film the bioreactor at different conditions and calculate the interfacial area that was observed. So the reactor had always a constant gas flow rate that is defined by the 1 ppm, and the power input per volume that is represented in watts per liter. It's how fast the reactor was steered in a simplistic way. And so what we could see is that faster we steer and more energy we put into the reactor, more bubbles were observed. So in order to quantify this area, in close collaboration with DTU Compute, they developed an algorithm that could determine all the bubbles in the videos and therefore determine the diameter of those bubbles. They've worked a lot on modifying the algorithm in order to detect the bubbles only and not double detections like we were observed before, and that was successfully obtained. With the data that came from this video analysis, I've used bubble size distributions in order to calculate what would be the average diameter of the bubbles in the reactor. But for that, it's not only important to see the number of bubbles, but also the area and the volume that those bubbles occupy. Because larger bubbles would have a higher impact on the area and also on the volume. So they also needed to be quantified. And in order to do that, so we could have a more accurate measurement, we've used this so-called Sauter mean diameter, which is a ratio between the volume and the area distributions. Based on that, we were able to calculate this diameter, and we could finally estimate a specific interfacial area. So, as you can see in this formula, this is the diameter, and then there's this little letter here that means the gas holdup. So this was a measurement that I've performed in order to quantify how much gas was enclosed inside the bioreactor. With those two determinations, I was able to calculate this specific interfacial area, which is a ratio of the interfacial area over the volume of liquid in the reactor. And we could see a correlation. As the power per volume increased, the specific interfacial area increased as well. And in order to compare it with the large-scale tanks, we actually observed that these values were within the range of mechanical agitator contactors. So at this point, I was able to quantify the kinetics of my enzyme, quantify the interfacial area, but then the question is, do they correlate? So what was observed is that the NOx kinetic stability actually correlated with the specific interfacial area of the reactor. And so I've represented that by the half-life of my enzyme, which means that it's kind of the time that it takes for an enzyme to lose 50% of its activity. It's just, so we want it to be high. Higher the better. So as lower, so what we would observe is that my interfacial area increased and the half-life of the enzyme decreased. And I've also tested air and nitrogen, and we can see a clear difference here. But before going into detail into this plot, trying to summarize the work that was performed, I established a scale-down experiments methodology for this part of my work, where we could, initially, we would think we can estimate what is the interfacial area that we would require at an industrial reactor. Therefore, we are actually able to mimic that interfacial area and expose our enzyme to that. And after incubating and calculating its kinetic stability, with the data, ideally, we would like to predict the stability of other enzymes under the same conditions. And so, therefore, we would be able to select operational conditions, improvements to the biocatalyst. But if we look more closely to this plot, what are actually the causes for NOx deactivation? So, if we look at the first part here, at low interfacial areas, we do see a correlation. So the specific interfacial area increases, and the half-life of the enzyme decreases, kind of in line with what was expected. And we also do see that nitrogen has the presence of oxygen, so the air, it's worse, so it enhances the deactivation. So this observation would also lead us to conclude that the presence of oxygen in the gas phase would enhance the deactivation of the enzymes. But if we do look at the second part of the plot, we do see that the interfacial area keeps increasing, but we reached a kind of a plateau. And this observation made me question what was actually happening here. What is really the interfacial area that was causing the deactivation? Because this interfacial area was changed with a change of power input. So mechanical steering may also have an effect that I'm not accounting for. So from this work, I've highlighted 3 different causes for enzyme deactivation. One is clearly the presence of oxygen, then the presence of gas-liquid interfaces, because we do observe that, and I suppose that, okay, mechanical steering may also have an effect. But in order to really understand, as one of the goals of my thesis, these parameters have to be investigated separately. So, on the other part of my work, I've studied the effect of mechanical steering alone on the kinetic stability of NOxes, so these enzymes that were used through all my study. But if we look at the literature, mechanical steering, okay, we do know that mechanical steering creates shear forces in a reactor. But are these shear forces actually the cause for protein deactivation? And if we go back in times, like on the 70s, they were suggested to be actually the cause for protein deactivation. But later on, other studies and other researchers have actually shown that other enzymes like ADHs, catalases, and ureases were not affected by shear forces. So there was kind of a controversy, what is really happening here? And then with this theory of the Kolmogorov length scale of turbulence, which shows that the size of the eddies when we have a turbulent fluid inside a tank, they are actually too big to cause protein deactivation, because enzymes are so small compared to the size of these eddies. They are maybe the size of my pointer. So how can that happen? So then, from all this debate, other very clever scientists conclude that, okay, maybe shear forces alone are not the cause. So when they are combined with another effect, they can actually cause the activation of the enzyme. But I still have the question, does mechanical steering alone have an effect on the kinetic stability of oxidases specifically? Because all the other enzymes that were tested, they did not actually require molecular oxygen. So is this the case? For that, I've tested different NOxes, multiple NOxes, in quiescent solutions, so no steering, they were just in solution standing on the bench, and different power inputs, so different agitation conditions in the reactor. And for that, and in order to compare it with the results that I've collected from my previous reactor, I've changed the reactor in order to avoid an interfacial area. Because we know, like as we do steer, the gas gets entrapped by the vortex of the steering. So in order to avoid any bubble in the reactor, I've made the lid coming down, as we can see here, because before it was here on the top, and I run the reactor with the liquid here in this position. So the reactor was overflowed. And therefore, I was able to change the mechanical steering without having the presence of a gas-liquid interface. And surprisingly, what we do observe was that the kinetic stability of NOxes decreased with the increase of power input. And that was very clear. And the same trend was observed for the whole NOxes, but in different ways. So, and it was actually very interesting to see that the kinetic deactivation constant increased. So the enzymes were being inactivated faster with the increase of power input. So then the question comes, if it is not shear, what could it be? So there were other studies with lysozyme that were done that suggested that when we were steering a reactor, there were actually molecular collisions that this shearing was causing. And these molecular collisions could be the cause for the deactivation of the enzymes. So they would actually, they also proposed something called a self-catalytic enzyme inactivation. So the enzymes would start deactivating, exposing their hydrophobic residues, collide with others, and increase the rate of deactivation in solution. So based on these studies, what I could conclude was that, okay, first, NOxes in solution, they do deactivate when I'm mechanical steer without the presence of gas. And we can also assume that, okay, as I increase the power input, the frequency of collisions is also increasing. So these collisions theory can explain the cause of enzymes being deactivated at, in a steered tank. So in a way, shear is not the cause, but indirectly it is. Because due to shear, we do have protein molecules to collide inside the tank. So after taking a look at mechanical steering, I was also interested to study. So, and if I just bubble, if I only have a gas-liquid interface, do my enzymes also deactivate? And this is quite tricky to do because normally sparging is associated with steering. So how could it be done? And so the solution was to use a bubble column that was previously developed by Pomerius. And so I went to Georgia Tech and I developed the same setup. So in order to have a very small bubble column, like you can see here, it's really thin and really tall, where I could sparge gas in the bottom and make the bubbles rise. And with these very confined conditions, the interfacial area could be estimated. And so this is how it looked like. So the bubbles were perfectly rising with the same shape. Thanks to these conditions, to the gas flow rate that I was introducing in the bubble column, I was able to calculate a bubble surface area. And after exposing the NOxes to this bubble column, to these gas-liquid interfaces, we did observe that as the bubble surface area increased, the residual activity of NOxes decreased. And it was also clear to see that the presence of air had also enhanced also the deactivation in comparison to nitrogen, which was shown before, so the results were in accordance with each other. So, and if we do compare with the no interface, so just the enzyme in solution, in quiescent solutions, no steering, no gas, we do see that just the presence of a gas-liquid interface has an effect on the deactivation of these enzymes. So, from this work, we could conclude that NOxes also deactivate in the presence of gas-liquid interfaces alone. But also the rate of deactivation changed from different NOxes. So I've tested more than one type of enzyme. They were all from the same, so they were all NOxes, but they were different from different organisms. And they all show the same trend, but at different rates, so different behaviors. And also, both air and nitrogen did also deactivate, and air enhanced this deactivation. And so these results also confirm that the presence of oxygen could be an effect. It is an effect. And if we do look so more closer into this issue, and in order to summarize the observed causes for protein deactivation in the presence of gas-liquid interfaces and mechanical steering, I've designed a regime plot that is a function of how we increase in mechanical steering and gas supply. And in the gas supply, we do so. It represents that we are sparging air. We are getting air bubbles inside the reactor, and they could be air or nitrogen. So here, the regions that I've highlighted, they do represent the half-life of an enzyme that is not adequate. And so, also from my observations, what I could also see is that, for example, if we do steer a lot, there's also a point, even though if I have a gas-liquid interface, that my molecular collisions will be higher and will be the effect that will dominate the deactivation. So all of them occur at the same time, but depending on where are our operational parameters, how fast we steer, which gas we supply, they will have a different importance in the deactivation rate. So then it's very important to mention that this regime map is highly enzyme dependent. So the boundaries are not static, they change depending on the enzyme. And this also leads us to hypothesize that perhaps this sensitivity of an enzyme towards an hydrophobic interaction could also be an underlying cause for the observations that I was seeing. So, to conclude this stability work, I can say that, okay, I've developed this laboratory scale methodology to study the enzymes in the presence of gas-liquid interfaces that can mimic the conditions in large-scale bioreactors. We could also see that the decrease of NOx kinetics were found to be caused by mechanical steering, presence of gas-liquid interfaces, and the presence of oxygen in the feed gas. So these three clear, distinct causes were observed. And we could also say that the deactivation is associated with this high frequency of molecular collisions that the shear applied to the reactor induces. So, like I mentioned before, and this is a very important point, is that the deactivation towards gas-liquid interfaces is still very enzyme dependent. And this fact made it very hard to predict. So in reality, we have to test these enzymes experimentally in order to know if they are sensitive or not. But so if we go back to the first question of my thesis, so how can we actually study these bioxidation reactions, taking into considerations the limitations that can be observed. And also, if we know that it is enzyme dependent and we do need to test the enzymes, the best way to do it perhaps is to develop a methodology where we could more focusedly approach these limitations. And so, based on these thoughts, that's what I've done. So, that's the first part of my title, the scale down. So, in order to develop this scale down methodology that I will present after this, I've based it on a scale down philosophy. And this way of thinking has been applied and used for the development of fermentation processes. And so these guidelines, that I call it for more focused scale down research, the first key step is so when we do experiments in the laboratory, we have to keep the process under the same rate limiting mechanisms as in an industrial scale. So the first goal is to identify what are the possible rate limiting steps in a large scale a priori, and then simulate it in the small scale. That may mean that maybe geometric similarity that we have learned that's a way to scale down experiments, it may not be maintained. So the laboratory equipment has to be designed in order to simulate these limitations. And so, and ideally, we would use the data collected to try to develop models that we could try to predict the behavior, even though it's really hard. And so then my work is summarized in this so-called scale-down approach, specifically for the development of oxygen-dependent biocatalysis. And so this scale-down methodology is driven by industrial targets. So the first step is to look at the industrial environment, identify what we need, so how fast our reaction has to be, how high the product concentration needs to have, so what are the limits that I can steer. So all these parameters that we can call it process metrics that will have an influence in the cost. And so after that, based on, so specifically for oxygen-dependent biocatalysis, I've divided the limitations in two main blocks. They can be more, but the two main ones that are very important and limiting are the kinetics and the stability. The stability was the one that I mentioned through my presentation. So if we do look at the kinetics, okay, after defining this environment, we have to perform these scale-down experiments. And so if we do look at the kinetics, one of the major problems that is observed a lot of times is the insufficient oxygen transfer rate. And so, but this factor actually improves with scale. So in small-scale bioreactors, we have lower rates of oxygen transfer than when compared to large-scale bioreactors. So based on this principle, what I do propose is, okay, the most important part is to run these reactions in the laboratory where we are not limited by this factor. Because we know as soon as we scale them up, this will be improved. So, and actually, oxygen transfer limitations may mimic other limitations in the system, such as stability. So we may think that nothing has happened, but we are just limited by oxygen transfer. So that is a very key point also on my methodology. And then if we look at stability, it's what I've explained. So we will have higher gas-liquid interfaces as we increase in scale. We'll have more bubbles in the reactor. So the enzymes will be exposed to more gas-liquid interfaces. So these conditions do need to be mimicked in small-scale bioreactors. And based on these principles, and then all the limitations we can identify, and ideally measure certain parameters, we could try to develop models in order to set targets for protein engineering, and also try to predict the in-process behavior at an industrial scale. So, to overview the possible limitations that can happen in biocatalytic oxidation. So this plot represents an operational window that is bounded by multiple limitations. So the one that I've talked today was about stability, that is represented here. So the presence of collisions, the presence of a gas-liquid interface, and we do know, like, as we increase mechanical steering and as we increase the gas supply, they will be harsher, they will damage more the enzymes. Then the second part is about the rates. Okay, then we can think, okay, we can fix stability, we just steer less and sparge less air. But in reality, there's a limit, because we do need to sparge and steer in order to having sufficient rates. So where is the trade-off? And so the oxygen limitations and the inadequate mixing represent the limitations related to rate. And of course, since we are talking about an industrial process, the cost cannot be forgotten. And there's also a limitation on how fast, how much energy we can input into a reactor, and also the percentage of oxygen in the gas that can be added, also for safety reasons. And so this plot summarizes these limitations and indicates an operating window for oxygen-dependent biocatalysis. It's also important to mention here that these boundaries are not well defined. This is it's an illustration. So there is a need to investigate these boundaries depending on the catalyst that we are using. And I believe that the methodology that I proposed here will help to a more focused research under this field. So, as future perspectives of my work, I believe that gas-liquid interfaces will come more often in industrial biocatalytic oxidation reactions. And the stability of the enzymes, it's really important, it's crucial. And so it will be needed to be studied. So, and I also believe that should be further investigation into this effect of the hydrophobic surfaces on the enzyme stability. Because if this is the underlying mechanism that is deactivating the enzymes, it can probably be addressed also using some protein engineering. But it needs to be understood, understand, and identified. And biocatalysis is also moving towards the development of cascade reactions with multi-enzymatic systems, and one of them may be an oxidase. So oxygen will be needed to be sparged and supplied having a gas liquid interface in that reactor. But not only the oxidase may be sensitive to these conditions, also all the other enzymes in the system may also be affected. So it is also important to investigate other enzymes when they are coupled with oxygen-dependent enzymes. And finally, with the great developments on the field, I also believe it is possible that we will also have biocatalysis move towards lower value products. And when we move to lower value products, the cost is a key feature. And for that, the biocatalyst needs to be very robust. So stability would become a crucial parameter for the broadness application of biocatalysis. And finally, I would like to make some acknowledgements. So first of all, I would like to mention that my project was part of ROBOX, a European Commission project that funded all my work. And so thank you to them. Thank you for funding my PhD. Then secondly, I would like to thank my supervisor, John, for all the support and very fruitful discussions, and also the opportunity to do this thesis. And I would also especially like to thank Matthias as well. Matthias was my supervisor during my thesis. He was a senior researcher, and he also was a great help and support. Thank you, and thank you for coming. And I would also like to thank the collaborations that I've done. So with DTU Compute, and also to Andy and Bettina at Georgia Tech, they accepted me to do my external stay. And also to Selecta, to Sebastian and Andreas, who supplied me a lot of enzymes, and we did collaborate really well in this NOx case. And then I would like to thank my friends and my family. Thank you for coming. I would also like to thank my friend and colleague Murray. He's not here, but we worked together on this project, and we have been through a lot of work and travel, and yeah, a lot of interesting developments on both of our projects. And finally, I would like to thank my husband, who supports me every day. Thank you all for your attention.
Thank you, Mafalda. It was very interesting. Congratulations. And let's say we'll have a break of 5 minutes. We'll be back at 10 to 2.
Yeah, no, I think I might have to cut it for that.
Quer. Mas eu sento-me ao canto, mas como é que isto funciona? Yeah, pode ser. Pode ser? We move here because they will not move.
I need a pen. Me too. Is there a mouse?
Yeah, there's more interaction. I actually have a chance to contribute just by carrying him back to the fence, so we can face taking the screen.
No, I don't think we could.
I think it's already.
I don't know what it is.
Full night now.
That's great.
Yeah, we feel pampered in that sense.
No, I do have a bottle of water on you. It's like, yeah.
Oh, you have it this weekend. It's this one, right?
Yeah, yes. Where is your copy?
On my notes, it says that you have to stand.
It does say that I have to stay. I think so. I mean, 5 minutes.
Yeah, I hear from my. Should we move the table and put them to sit?
Yeah, I mean,
A little bit. I think that
you
could be
want
good,
to,
yeah?
and we just,
Yes.
yeah,
I think that would be good.
yeah. Tell me how that, I mean, but if it is too boring, maybe I can also.
Well, Shane, what do you
It's
prefer?
okay.
I don't, I'm flexible. Whatever, I feel the I'm fine.
you up front here.
Ron, you decide.
I'm John Severs from the defense.
No, here. Okay, so then I could, we thought maybe you could sit up front, if you don't understand, you can sit. I think it just makes it a little bit more.
Forced migration.
Already outside.
Yes, that's exactly what I'm doing as well.
All right, guys, we're moving the stream a bit. Anyone who's still watching? Sorry, we're migrating to this side. Just so that we can try and
You want to sit behind?
Ooh, it's going to be difficult.
I'd sit here with this.
It's going to be very difficult to get all of them in there.
Sure.
We may, yeah, no, it's going to be almost impossible to get the whole setup, but. Okay. Yeah, I mean, that's about as good as we're going to get, unless we can, let's move this table a little bit up. Yeah, we're just taking this table a bit further out so that I can get a better angle on. Just push it.
I'll sit next to you.
What? Push it. No, it's just the noise. The noise on the stream. Sorry, headphone users. Okay, now move the kettle and.
We also part of the examination.
Perfect.
So you want, John, you might want to move as close as possible.
You can also come to the side. Say hello, I guess.
And the witness doesn't talk.
Ideal, but at least you can see all three. All right, guys, remember to smash like.
Okay, so we'll start.
Yes, so I have the honor of leading off. First of all, very happy with the presentation. Could you turn to overhead 39, please? That's the pages. If you have the presentation still,
Oh, sorry. Yeah, I do.
that would be just as good, better. And I noted overhead could have been 39 or 40. I'm basically looking at the tape. Yeah, it's 30,
This one?
39, yes. So this is a nice sort of summary slide. What I wanted to ask you about is you have essentially, you write no interface, and then you write quiescent conditions, 210 hours half-life.
Yes.
Then you give us 2 data points with sparging, i.e. with interfaces, with 2 media, nitrogen, and I guess oxygen here means air.
Air, yes.
But what's missing is the control experiment with no interfaces, but under stirred conditions.
Yes.
A, do you have a data point, a half-life number, and if not, could you estimate that based on your 3 data points that you do have?
I do. I think I have it on my thesis as well. I don't know the number in the back of my head.
I have to check up as well.
I can just take a look. Yeah.
Okay. Do you
But
recall
yes.
off the top of your head roughly what the number is?
I think it was maybe around 100, but
Okay.
I'm not sure.
Yes.
I know it was lower than that. I can say it was lower
Yes.
than no interface,
Yes.
and it was higher than
Yes.
partial.
Yes. And
That was-
that's already sufficient for me. We'll find the exact number somewhere
Yes.
else. From those 4 data points, could you assess or reassess sort of the answer to your own question? You nicely prepared sort of the fact that there are three influences you studied.
Yeah.
One was just mechanical stirring. The second one was the presence of gas-liquid interfaces, and the third one was the presence of oxygen. I think you inverted those 3, but doesn't
Yes.
matter. Could you, just based on those data, sort of assess/reassess what the most important influence is, if you look at this just from very far away?
If we just look, if I would just have done these experiments and look at this data, the way you were showing, from here we could say that if the half-life with just this steering would be around 100, let's say, we would say that the presence of the gas liquid interface would have a higher effect compared to steering.
Yes, yes, I would certainly agree with that.
That's, that would be a conclusion from this observation.
Yeah.
But I also, the way I've done that experiment, the one with steering here, was just a magnetic steerer in solution. So the steering was also not as harsh as the steering that I've applied when I run the experiments in the reactor.
Yes.
And I also believe that that may have an impact.
Yes.
Yeah.
Yes, it's interesting. If you now could turn to slide 24, please.
Yes.
You have a line of inquiry that deals with sort of your correlations between P, the power input per unit volume, P over V, and A. First question, so in your thesis, you look at this plot and conclude that there's an exponential increase of the interfacial area with increasing power per unit volume. I look at these data points and could make a case that it's linear. So A, what is the data situation telling you, and B, do you potentially have any kind of mechanistic models that would tell you which of the 2 is the better answer?
So first, what the data for sure tells me is that the area increases as I put more energy in the reactor.
Yes.
That's clear.
Yes.
So the behavior is not clear, and I do not have a mechanistic model to prove that. So they do increase, maybe claiming that is exponential. It's just a supposition. It's not based on an analysis.
So you did not write that into your thesis because you were aware of a model that explains it with an exponential effect, but just didn't put it in the thesis?
No, I did not do a model.
Yeah.
So I've observed it, and we could see this increase, and that was what was required in order to compare the data sets. And it was sufficient to show the effect. So it will be interesting to try to fit a model to this data, but for that, I would also need to have more experimental data.
Yes, so there's no question that, what would, by the way, just what would you do if you sort of had all your tools ready and wanted to show whether this is exponential or linear?
I mean, first I would repeat each one of them. So I could have a data, an error bar.
Are these all equally important in the consideration whether you have a linear relationship or an exponential one?
No, I mean, I would have to try the first ones also. So we could see if the decay would be like that. And
Okay.
then, yeah, and then I mean, maybe more in the upper level probably.
Well, definitely, because for I guess for two reasons. A, because you have a sparser data set as far as the population on this plot goes, so that immediately suggests that this would be the way to do it. On the other hand, you should also plot this in a non-linear fashion, logarithmically, in other words, to check the fit of an exponential one. But certainly, I mean, currently, in my view, and this is not atypical, the impression that this is an exponential increase mostly hails from the precise position of your uppermost data point at, what is it, 320 per meter interfacial area and 5 watts per liter. If that data point was lying somewhere else,
that's true.
it might have said it's linear. So it hinges on that region, basically.
That's right, and also it's also important to mention that at higher power inputs is also where the method had more errors. So the estimation for the bubble size diameter, it's harder at higher power inputs. So definitely that data point should be investigated.
Yes.
And that could change the shape of the curve.
Yes.
The curve.
Yes. If you now could turn to slide 33, please. Or maybe 34 it was. That was the linear relationship you coaxed out of the data, which is very nice, between your deactivation rate constant, KD, and the power input per unit volume.
Yes.
So those two are linear. You sort of also have done the specific interfacial area, lowercase a, over the power input per unit volume, P over V, which is linear / exponential, depending on how we look at this. And could, from that one alone, could you already have made a prediction how your effective deactivation rate constant KD changes with the interfacial area?
If I would base on these?
Yes, if you just combine all these insights.
Yeah, I mean, the way I've calculated the interfacial area was based on changing the power input. So the deactivation rate constant, I think they could have here they would be more linear if we compare with the previous data set. So definitely the 5 watts per liter data point on the previous plot would have to be reconsidered.
Yes, well, I completely agree with that, with this data situation. Now, if I can ask you one more time to switch over to 39 or 40, slides 39 or 40, that's the situation where you plot your deactivation rate constant against the interfacial area.
29?
39 or 40.
Yes.
It's 30, yeah, and if you push the button here so that we get the. Here, when we look at these plots, we immediately say, this looks like sort of negative exponential behavior.
Yeah.
Until we read that this is residual activity over the bubble surface area.
Yes.
Couldn't you try to get data not just as KD in per hour, but also a deactivation per incremental bubble area?
Yes, that can be done.
So I would suggest that you do that because you have the data, right? Should always interpret your data to the fullest.
Yeah, I understand. Okay.
Not further, but not less. So, ultimately, while I obviously would argue that the deactivation rate constant per unit time is very important, ultimately here, what you also like to figure out is how does that deactivation take place over the course of
Per
accumulating
square meter,
interfacial area?
Yes, yes. Yeah, I would agree that that would be interesting to see.
My last question in this round is sort of one that I probably should have asked first, but I'll ask it anyway. So you say you want to study all these phenomena with the parameters power input per unit volume, and also sort of what I would interpret as gas, call it gas holdup, gas input, gas flow rate. And I fully agree with that approach, but there is an assumption behind this, implicit or not, why this is important. So could you maybe come back to why you think that P over V and gas flow rate are important here?
Yes.
In other words, I want to hear from you the picture that we all have in our head. And more specifically, I want to hear from you that there is a correlation that we all know that is implicitly at the bottom of all this, or maybe at the top, at the starting point, while we all think that this is those two parameters, P over V and the gas flow rate, are really the driving force.
Yes, so P over V relates to the the equation that I believe you're mentioning is the one that correlates it with the steering speed. So how fast we do steer a reactor.
Yeah.
And so that's depending on the diameter of the blades also are implied there. So that implies the geometry of the tank.
That's correct, yes.
So
absolutely.
in order to compare these two regimes that I'm talking about, like the small scale and the large scale, the power per volume is the way where we could compare the two scales in a better way. Because if in a smaller scale, the same higher power input will imply a different steering speed, depending on the size.
Yes.
So that was the reason why I've chosen it.
Okay, but now sort of, we ultimately agree that oxygen transfer here is needed before oxygen uptake, which in this case is manifested by the proof of activity of your enzyme here. And oxygen uptake, how do you characterize oxygen uptake?
The moles of oxygen consumed per power?
Yeah, but I mean, what characteristic quantity are we typically talking about?
The KLA?
KLA, like KLA. So if you now say, okay, you have KLA as sort of an important characteristic here, and you link that to power input per unit volume and gas flow rate. If I now started to argue and say, oh no, I think there are different parameters that would correlate to KLA, how would you shut me up?
I mean,
what would you tell me?
No, I would tell you that these two are the ones that have a higher influence, for sure. And they will affect the specific interfacial area.
I agree with you.
Okay.
What's the literature source? What's the sort of which name? Where would I have to look up to convince myself that this is indeed correct?
Which authors?
Yes, that KLA is actually correlated with P over V and gas flow
Alvin
rate.
Nino.
So what?
Alvin Nino. You would look into his literature.
Okay, maybe
And
I'm asking a
that's-
question that's so obvious today that nobody again looks at the source. There's this, by the way, and I'll ask questions in the second round on the dirty versus clean interface, coalescing versus non-coalescing bubble situation. It's not that long ago that there was no correlation that people agreed upon, whereas now it's that correlation that I'm referring to.
From Van Trier?
Van Trier, yes, that's what so we all basically buy
everything is based on that.
the picture, and that is nowhere apparent in your thesis. So, and I think it's useful to remind ourselves that basically the thought process that went into what Klaus van Trier then coagulated in those basically two correlations, because one was for clean interfaces and one was for dirty, so-called dirty interfaces, that's at the basis of what you're doing.
Yeah, for sure.
That's our rest.
All right, so I've told this to John before, I'll tell you, I'm super excited that you're actually working on this type of problem. I spent the last 7 years of my career doing industrial biocatalysis, specifically worrying about oxidation reactions, and really struggled through a lot of these same concepts, so thank you. I'm going to kind of follow up on Andy's last comment in a slightly different way, because to me it's maybe a little bit less obvious why that's exactly the right equation you should be using, right? And I want to be really clear why. And I think one of the, as I was reading your thesis, I was listening to your presentation today, I think one of the things that really jumped out at me is the inherent assumption about bioreactor execution. As a company, we don't do biocatalysis in bioreactors. We might be the only company that doesn't do that. But a lot of the work that I spend my time doing and what our group spends their time doing is really kind of optimizing processes for stirred tank reactors that would be traditional in a synthetic chemistry arena rather than a bioprocess arena. So a lot of my questions, to give you a little heads up, are coming from that vantage point, coming from a vantage point where the reactor is very poorly designed. So, I guess one of the questions that I would have is, kind of philosophically, how do you go about distinguishing between, when you have a really well-characterized reactor and when you have a really poorly characterized reactor, right? So in a reactor where you might not have, where it might be so poorly defined that it doesn't follow the classical expressions that exist, how would you think about the methodology that you've developed here being applicable where the models start to break down? Like experimentally, what's your strategy for how you go about doing that?
Yeah. So, like I mentioned on my scale down approach, the first key thing is to identify those rate limiting steps that you do have in your bioreactor, in your reactor in this case. So I would look at that, okay, this is what we have available, and these are the conditions that we can have in a large scale, and that use that, even if it is a small characterization, you would know how much energy you can put, and you would know how much gas you can put. I think it's present in both ways, and transfer that information to the lab, and then we don't need to use a bioreactor. We just need to use a reactor where we could simulate that rate limiting steps, and that's why I believe that my approach is not only applied for these very well-known Russian turbines, characterized reactors where we all know their correlations and so on, but it's also very applicable. And I also believe that the way that I propose it, it gives flexibility to the way you define your problem. Because what I'm trying to say is that we just have to identify what are our constraints. And then based on that, we will try to mimic this in a small scale. So in that sense, I think it's very applicable.
Maybe kind of building on that, you talk a little bit in the thesis itself, kind of the methodology that you use to, so core and central to a lot of the things that you talked about is power per unit volume, right?
Yes.
So, and correct me if I'm wrong, but as I interpret it from that is a calculated power per unit volume based on geometrical parameters and color, type, and shape. So some of those, so are there experimental ways that you could determine power per unit volume?
Yes.
Are there instances where you are aware that those correlations start to not make sense or start not to be valid? Because that's actually a really important piece that it would be really helpful to hear kind of what your perspective is there.
So there are ways you can measure the energy you input to a reactor. I just didn't have that tool in the lab. So the only way I could do it was to measure the steering speed. And so in that way I used that correlation that correlates the steering speed with the power per volume to give me what the power per volume was. So that's why I've done it that way. If I could measure it, it would be more interesting. I also agree with that. But then it also differs a lot, trying to answer to your second question, on the conditions of the liquid, so the viscosity and if you have solids and all that fluid dynamics, let's say, fluid characteristics have an influence on those correlations, and they will not follow the clear trend, let's say. So that's something.
Can I sort of just ask friendly intervention? You did not, it wasn't apparent in the thesis, and I think I understand why. You could or did not measure the torque on your
I did not measure.
Yeah, that's feasible in principle.
It is, I
and I think would get you out of the rut of needing to justify constitutive models for your fluid.
Yes.
Now, I will openly admit that was a little bit of a trap on my part, because yes, you can measure the torque, but that's actually wrought with a lot of challenges. Like, so one of the things that's really hard to account for is like heat dissipation, whenever you're measuring, when you're physically measuring the power.
Yes.
Yeah.
You can. Yeah.
You end up, most of your power is lost to heat rather than.
Yeah.
to-
Exactly.
Okay.
But, one of the things that we've always experienced is below about a liter in scale. And this is why this is kind of an interesting topic to me, because
Yeah.
below a liter in scale, some of those correlations start not to hold very
Yeah.
well.
Mhm.
And I think one of the outputs of that is certainly if one of the central tenets of your thesis work is to really do scale down at a scale appropriate, you do have to be really mindful about how you kind of manage stuff.
Yeah, that's true.
Can you go to, it was one of the ones that Andy, I think it was page 24?
Page
Or
or
slide 24.
Okay.
Slide 24. Actually, no, it wasn't. No, that's not, that's one. Yeah, so I guess the question that I have here is you kind of hinted at it in the last question, but obviously in the calculation for P over V, you do also, one of the challenges with measuring torque, for example, is as you start increasing the gas holdup substantially, you have you have a significant drop in the torque that's actually, in the power that's actually measured at a particular agitation rate. Can you comment how correlated A and P over V are, little a, a specific surface area are, and power per unit volume when they're kind of presented in this way? Meaning, at really small specific surface area, do you see, is the result different, comparing one particular power per unit volume or not? Like, how do you decouple both, P over V and A, I guess is my question.
Okay. In this case, it's not possible to decouple both, because as faster you steer, you will have more bubbles in the reactor. So that's why one implies the other. So they are correlated. And definitely, like I was answering before, I should definitely also, maybe if I would remove the last stated point, the observation would be different. They would probably increase linearly, right? But they are impossible to decouple. So especially in a stirred tank reactor. So.
Just as a thought, again, what just comes to me as I'm listening, if you had to do this for fermentation, at least the faculty among us squeeze the students all the time on this thing, so might as well now mention it in a real thing here, is the ungassed power number situation, right? Where it's like a Miller correlation comes to mind, so where you investigate how the power is related to the amount of gas you have.
Yes.
And it turns out the more gas you have, the less
Less
power
power.
you need, because stirring
Yes.
gas is easier than stirring liquid. So possibly you could investigate how this feeds into your situation here,
Yeah.
where of course you don't have any cells and stuff.
Yes, no, but definitely that can be looked into.
I guess one other question on along a similar line. So I don't remember, I know I saw this in your presentation, it's certainly in your thesis on page 54. I think it was maybe, I don't remember exactly what, it's on one of the slides too, so you're welcome to pull it up on a slide.
It's the power input and the deactivation rate
exactly,
constant.
deactivation rate.
Yes.
Yeah, so like I started, so we don't work in bioreactors in our space, which also means we don't use RDTs, ever. We don't use Russian disk turbines.
Yes.
Ever, right? So, we actually do a heck of a lot of work in impellers that you would look at and be totally ashamed that we're trying to do biocatalysis in, especially oxidation. Can you explain to me how this curve might look different if you were using a pitch blade turbine type reactor, or an anchored impeller, or something that is not an RDT?
Yeah. So a Russian turbine, it is the way. So the different turbines will have a different effect on the fluid inside the reactor, right? The Russian turbines are known to have that beautiful, very well mixed system, and especially in a small scale, that's really observable. So the regime will be different. So if I do correlate that, if I do say that the deactivation is the deactivation rate constant in this case increases with the increase of collisions, of frequency of collisions. If we would use other impeller, the deactivation rate constant would probably be lower because we would have, I would assume we will have less collisions in the media and they would decrease. Now, if they would increase linearly or not, that's very dependent on the blade. I could say that probably the plot could shift down, something like that, or also as we increase, we do not increase that much the regime inside the fluid, so maybe also it can angle a bit down the correlation. So that's what I can extrapolate.
And then maybe, I know I said that was my last one, but just building off that really
Go
quickly. One of the things that, missing isn't the right word, right? But certainly I'm looking at it through a slightly different lens. And one of the things that we're very constantly cognizant of is, so under-baffled reactors, which is, again, is a really big no-no, but it's a reality in almost all of our cases. So I'd like to hear your comments about kind of baffling and what its impact is. But then also, bubble pattern is actually really important. You kind of alluded to it in your last response, right? So RDPs have really well characterized recirculation patterns that are really ideal for gas holdup, which is why they're used in bioprep. A PED, like a pitch blade turbine, for example, is designed for vertical pumping. Can you comment on how good or how bad that would be and what impact that has on, for example, bubble lifetime and how bubble lifetime figures into this?
I mean, I would assume they would be less retained inside the tank, so they would just move, rise faster. So in a way, you would have less gas, like for less time. So a lower gas holdup, if we could measure in that way, in the reactor, and that would affect definitely the gas transfer. But I did use baffles, but in my reactor, so we could really see the homogeneity. But yeah, it can also be done without. It's just a matter of trying to simulate that.
May I make one very sort of positive comment? And I do this because in a totally different context, I'm involved in another image analysis situation where the question is depth. How do you resolve that? Your decision to take a Russian turbine, which is like a radial impeller, so you push away your bubbles after they come out of the sparta on the same sort of height in your reactor, in contrast to like a marine impeller, which is famously designed to push the boat in axial direction, basically. This choice of radial impeller was absolutely smart and probably saved your whole image analysis situation. Because what would happen if you had vertically rising bubbles in your field of vision of your probe is that you would never know how many bubbles you have behind each other, and your depth resolution would have been incredibly more challenging.
Yes.
To the point where your partial differential equations to then figure out the actual surface area would have been pretty much unsolvable. So this is a great choice, and this is why your data actually looked that way. If you hadn't done that, you would have been in probably not.
Yeah, I mean, that was a very key feature on the way the experiments was done, was where the probe would be placed, because it had to be placed on precisely half of the turbine. So the bubbles, otherwise we wouldn't see them, because they were just like pushed like this, and if you place it in the right spot, we could capture those images.
Yeah, and in a vertically pumping impeller, which again, in almost all cases, our reactors are designed to suspend solids. That's what they're designed for. They're not designed, right? And that's a problem we have all the time.
Yes.
And it's impossible for us.
Yeah.
Okay, it's me now. Okay, I'd like to start too by saying that I enjoy actually so much the reading of the physics. I have been working actually with some of the enzymes that you mentioned here, especially glucose oxidase. But I use the enzyme a little bit as a team, you know. I didn't go into the basics. So it was really nice actually for me to know a little bit how the enzyme works. I can recognize actually the difficulty of the thesis as well. Especially you need to get familiar with so many methods here. I think each of the chapters practically is a different method, a different configuration of the reactor as well, so there is a difficulty there, I guess, right? I'll start by framing a little bit the project, asking two, well, I have three questions actually, but I will start actually by two at the beginning. Okay? The first one is actually, I know that you talk in the thesis in many pages of the thesis that you cannot generalize, right? That the results change with the enzymes. But you know, I'm curious actually to know how much can you extrapolate this data in the sense, do you think it's possible, for instance, to say, okay, so we have this enzyme with this structure or with this, I'm not an expert actually in enzyme composition or structure or blah, blah. So you have a certain composition, a certain structure, and you can relate that to the behavior of the enzyme. So you can generalize the behavior and to predict it somehow. This is one of the questions. And the second one is, I think we talked about this actually before. You changed the enzyme, you started actually working with glucose oxidase, and then you changed to NOx. Why didn't you continue actually with the same enzyme? Yeah, it would have been easier, right?
Yes. So, to answer to your first question, that's what I aim for. So I do aim to be able to understand what is actually the mechanism. So we would be able to look at the protein structure and say, okay, there are these certain amino acids. If it is hydrophobicity, maybe this enzyme would deactivate more or less. But from the results that I do have, I cannot extrapolate. Because
But it is possible to do that.
I believe if the experiments, so one very key thing here is that all my experiments were done with the crude extract, so with self-extract enzyme. So they had all other stabilizers that we don't know the effect of. So I cannot correlate that with my enzyme itself because whatever is in solution can also be causing a stabilizing or destabilizing effect. But one of the future works that I also proposed is that if we could use these enzymes or a certain enzyme that is purified and we can expose to these certain, to all these parameters, the gastric interface and so on, there are more possibilities to measure other effects, like also if it is, in the case of oxidases, if the FAD, so if the cofactor that is covalently or not bounded and it is affected or not. So I believe there are ways to do it, but it will be extremely hard to do it. So my guideline for that is to actually try to investigate in a very confined way if hydrophobicity is the major cause, and if that will be the cause, then we would be eventually able to look at the structure of a defined enzyme and probably have an idea if that will have an effect or not. So that's what I believe. I couldn't do it, but and yeah.
So I think you actually make a convincing argument, even though we have few data points, which is due to the fact that you only have 3 NOxes from Selecta at your disposal. You don't count our own NOx5. But I think you make a fairly good argument in your thesis that protein engineering for the purpose of stabilizing the enzymes under mechanical stress of any kind that you investigate so far has not yielded lots of results. Because if you compare data that, for instance, read your half-life of your wild type is 12 hours, the half-life of your best of those few variants is 18 hours, from far away that looks more or less the same. So to start protein engineering efforts to stabilize the NOxes at this point is a very hard problem. I would go as far as to say we have no clue what we're doing. Point one. Point two, what you did not at all look at, of course, is the chemical reasons why these deactivate, which are apparent in the fact that even under quiescent conditions, very benign, your half-life of towards deactivation is 210 hours. If you look at Shane's conditions, and maybe you get away with that because you make sort of few valuable batches, but if you ever think of making sort of more commodity type products, a half-life of 210 hours is laughable. I mean, that's not something you could recommend for large-scale use. So we need to go even further back, and then there is a published published causes of the inactivation of NOxes out there. That's essentially overoxidation of thiols in the active site. So protein engineering, if at all, would have to focus on how do I limit the overoxidation of the thiol in the first degree, because that really is sort of the order of magnitude difference that we see, whereas the other influences are important, but they can't be tackled from protein.
So I guess maybe I'll jump in as well. I have some perspectives that might be better Andy and I shared them over beers. But I guess maybe a question that I would kind of turn that into, right? So if I think about protein engineering and what its strengths are, right? One of them is the ability to do it in high throughput. From everything you've learned, why is that so hard? Why is it so hard? Well, I mean, what Andy just said, I fully agree with it. It's incredibly hard to engineer for protein stability.
Yes.
Why?
What I believe is that we don't know the cause. So how can we tackle the problem if we don't know the actual cause? Because like the interaction with an interface, that's an observation, is an effect, but what is actually changing on the protein? We cannot measure it. So how can we modify something through protein engineering if we cannot target what we want to change? And that's what I try to aim for, and that's what I believe the road should go, the way should be. So.
And is a 96 or 384 well plate the right platform to study these things?
I don't think so. Not at all, right? That's also lab, but I think that's more for screening, I would say. So if we want to investigate these causes that are like actual problems when you do scale it up, they need to be studied in a different way in the lab. And but trying to answer to the second question that you posed, Manuel. So glucose oxidase is stable in the presence of gas liquid interfaces. So and that's the reason why I did not study it. So there was no effect, at least as the extent as NOxes were seen. So in order to show.
So even if you increase the agitation, or
it's very stable. It's a very robust enzyme. It's very, very stable. And also, I mean, NOxes are, there are less robust enzymes, definitely, in comparison with the GOX that has been developed for years and years and years. And so if I wanted to see the effect, I needed an enzyme that would deactivate, and NOx was a great candidate. But I think this result also shows that two oxidases, they are even within the same enzyme class, they have a completely different behavior. And so that's why.
I think though there's a kernel of hope in this thing. So yes, glucose oxidase and those NOxes here belong to sort of at least a reasonably close class, although I'm not sure that it's single thiols that are present in glucose oxidase. In any case, they're not, I mean, they are fairly close enzymes. If a certain amount of prior research has resulted in a stable glucose oxidase, we could infer that if we just did enough high-level, good quality research on NOxes, we would be able to stabilize the NOxes too. How to do that, that's what we're discussing here. But so the perspective is actually not that bad. I'm not aware of how the early glucose oxidases behaved. But you're absolutely right in pointing out that one is sort of fresh out of the discovery stage, and the other one has been around for decades and is in industrial products and diagnostics. Right? So they've been really investigated in a big way.
Okay, I have another question. Can you tell me a little bit? This is curiosity. I don't know myself. So you mentioned that these NOxes are used actually for factor regeneration, right? But we have other options as well. For instance, I remember one of my students was using dehydrogenase as well to regenerate the NAD+. So, you know, the question is, if it's so difficult, actually, if the enzyme gets deactivated, actually, by so many reasons, you know, oxygen, mass transfer limitations, interfacial, you know, the limitation that we have is actually that the substrate, that this lactic acid dehydrogenase that we were using was actually very expensive as compared to the product that we obtained to regenerate the NAD+.
Okay.
So can you tell me a little bit about the advantages and disadvantages, or what are the ones that are most used nowadays for cofactor regeneration?
Yes, so one way that can be used with the ADHs is to use acetone. Then you can recycle the cofactor in that way. And then also, yeah, and then also that enzyme. But all of the, so, and also, I mean, you can also use the ADH in the other right direction and have it itself recycling, right? Because the ADH works in both ways. So, but the problem here is that we want to be favorable towards an oxidation reaction. And ADHs kind of prefer the other way. So coupling with NOxes would actually improve, I mean, thermodynamically the reaction would definitely move towards an oxidation direction. And that is one of the great advantages of coupling these two enzymes. So that's why this is such an interesting case, in my opinion.
How do you control that? You just mentioned, for instance, alcohol dehydrogenase. Imagine that you have, I mean, formaldehyde and methanol. You know, how do you control actually that the reaction goes in one way or the other way? Is just the presence of the substrate, or can you control something else to control the direction of the reaction?
Can control. You can, depends on what you're producing, but you can. If the ketone would go forward, you can probably control pH because we'd make an acid. But that could be a way. But if you do have a NOx, as long as you have oxygen, your reaction will move in that direction. But the way I would do it, I would measure my product concentration in the reactor. And then I could know if that was being full.
Yeah, but how to push it in the opposite direction is a little bit my question. I know that you can measure it, but,
yes,
but how to push it in the reverse direction?
Which one of them?
For instance, imagine that you are producing, from methanol, you produce formaldehyde, and you want to do the opposite.
You don't want to.
You want to do the opposite, from formaldehyde to methanol.
You can remove the product as long as it's being formed. So you have excess of substrate, for example. So you have like an in situ product removal operation, where you're just removing your product, so your substrate is in excess, so we would go in that direction, for example. That could be a strategy.
What we did with this enzyme, I don't know if you know this system, guys, is to modify the pH. It seems actually that if you increase the pH,
which is also product, which is partly product,
right?
Yeah.
Yeah, removal of
Yeah.
the proton.
Yes, yeah, that's true.
So maybe just a comment more than anything, building off of that. So one of the things that we really like about NOxes is they don't go the other way. Right?
Yeah.
So obviously when you're trying to drive to an oxidated product, that's great.
Yeah.
But their equilibrium is so far in the oxidation direction that you don't really have to worry about NOxes.
Yeah.
Agreeing with that, quick question sort of while you're sitting here. Have you ever looked at the equilibrium of NOx-driven reactions?
No, I've not.
Neither have my students who work with this, which is always pummel them for. But
I've not.
everybody seems to be so comfortable with the notion that these are more or less sort of irreversible reactions from oxygen down to water.
Yeah.
I remember the time when we were as comfortable with that kind of thinking with formate dehydrogenase regeneration in the opposite direction, where you take formate and produce oxidize that to CO2. Oh yes, this is an almost irreversible reaction, blah, blah, blah. Until we now are faced with the notion whether that's good or bad, ridiculous or useful, it should remain open here, that folks get money for using CO2 to be reduced CO2 out of the air using formal dihydrogenase. So they do turn this around, and the equilibrium is 10 to the 5th or something like that, which for our purposes here, gathering high conversion is enough because it's 99.9 something, so we don't need to worry about the remainder. But it would still be interesting at some point that somebody gets some idea about where the equilibrium in NOx-driven reactions really is. Whether computationally or experimentally or whatever, but this notion that we always sort of claim is basically irreversible, which I believe it is, I'm not saying it isn't, but it's not substantiated.
Yeah.
So we've at least tried. Yeah, we haven't been able to measure.
That's good news, both of these.
Okay, I have just the last question in this round. So we have at least 4 different mechanisms here limiting the activity of the enzyme, right? We have the mass transfer of the oxygen from one phase to the other phase. We have the stirring. We have the interface, gas-liquid, and then we have the presence of oxygen as well, right? So can you predict a little bit? I know that you say in your thesis that you haven't immobilized the enzyme. You know, imagine that you immobilize the enzyme on a membrane. Considering actually these 4 mechanisms, can you guess a little bit what will happen to the enzyme, to the activity of the enzyme? Yeah.
So the rate will still be a problem because we just added one more barrier.
Yeah.
So the transfer will still be a problem and maybe a big problem. Depends on the membrane, of course.
Yeah.
Then, of course, the enzyme is not exposed to all the other factors because we steer, but it's just immobilized support that is exposed. So if you expose like an enzyme in a certain support, then you just put it in like solids in the tank. So the enzyme will not be exposed to the gas-liquid interfaces, neither the oxygen and so on. But the steering can also damage the support, and that can also be a problem. But the rate would be probably the major one, I would say. So, yeah, but the activity of the enzyme would be, I mean, in order to have the same activity, you would have to load your support with a lot of enzymes. So maybe that would not be enough to justify the cost of that immobilization.
But I agree with you. I tried to immobilize the glucose oxidase and it was a disaster.
Yeah.
So one of the things that we find is once you actually immobilize a protein, once you have an immobilized enzyme, anytime you introduce a gas-liquid interface, you no longer have a liquid contacting enzyme. That's the problem that we have. It's really hard to rehydrate a dehydrated support.
Yeah.
That's the problem that we've had.
And the reactions will be much slower at this.
If you look at this from the Kolmogorov scale argument, why could immobilization be a really bad idea?
Yeah, I mean, that would be a size that would be affected by the eddies.
Right.
Definitely.
You actually move your small little protein that is definitely smaller, much smaller than your eddy, onto a surface where the question of Kolmogorov length scale isn't that simple, but where you could easily argue that it's actually now within the Kolmogorov length scale, which means your shear actually damages your protein, or potentially damages your protein.
Yeah, like.
Okay.
That would be.
Second round.
Second round?
Yeah.
Okay. Well, it's me again. I want to follow a train of thought, but before we do that, can I ask you about table 7.5 in your thesis? Sorry, 7.4, page 86. And yes, we should be probably having it in front of us.
So.
Page 86.
What was it?
Page 86, table 7.4.
Yay! Done. It's not happening. It's one of the hardest things I have.
Yes, so you here have KLA under coalescing and non-coalescing conditions.
Yes.
Reading your thesis, this data sets appear to be sort of almost pulled out of thin air. Could you comment on how you got those numbers?
So they are from a reference from
Okay,
Norman 2016.
okay,
And and it just, it's based on, he assumes he assumes the same power includes the volume and the same PVM. So it's a calculation.
Okay.
So it's using the correlations,
okay,
the Van Fleet correlations
yes,
for
Yes.
coalescing and
Yes.
uncoalescing conditions.
yes,
And so just based on those calculations,
yes,
those are the numbers.
okay,
So they are not experimental numbers.
okay, so they're purely calculated from
They are,
both of Van Riet's correlations?
Yes,
that
they are
replaced,
theoretical numbers.
reproduced in Norman 2016?
Yes.
Okay, that's what I thought,
That's where
because
come from.
somewhere, if they had been measured, you would have had to comment on that. Okay, so, do you believe that?
It's hard to believe. Actually, it's hard to believe because what we see is that under coalescing conditions, the KLA actually increases with K, right? But then under non-coalescing conditions, the KLA appears to be quite constant over
Mhm.
scales.
Mm-hmm, mm-hmm,
I was surprised when I looked into this data.
mm-hmm,
Because I mean, my tank, it's I assume it was non-coalescing conditions, the one that I had.
yes, very good, right, that's, and that would be my next question, so yes, you actually demonstrated to us
Yes,
that you have well-formed bubbles that they don't change shape, and at the end of the day, that's those are non-coalescing conditions, which actually Van Riet referred to as dirty solutions, which we can interpret to mean there's actually salt in the solutions,
yes, there is salt.
right?
Yeah.
And that's,
Protein.
so the clean conditions a la Van Riet is almost like basically pure water plus gas, and we don't have that, we have salts in there, these, obviously. Now let's look at the KLA under non-coalescing conditions, which is the relevant stuff, I think, not just for your data, but also for generically operated reactors. Forget about the coalescing ones, they're not so important. And you look at those 5 data points. What's sort of your impression, and do you sort of comment, do you agree with that, and what's the implication here?
So, and that's where I, in a way, for the solutions that we are talking about, because we do have salt, and even more important, we do have a protein there, and with tons of, I mean, if it is a sulfate extract, there are a lot of other compounds there, and
Yep.
I believe that all of that does affect my KLA. And
Fully
so,
agree. Would you expect
with-
that to lower or increase the KLA?
with the scale,
No,
be
no,
lower.
no,
I would
no.
expect it
If
to be
you
lower.
if you take any reactor scale,
yes,
let's just pick the 0.01 cubic meters, and so you're 518 per hour, non-coalescing conditions, but without any protein present. That's what Van Riet
Just-
actually,
just water, yes.
just this water with possibly some salts or other stuff, but definitely not large molecules such as proteins. If you now stick protein in there,
yes.
would you expect this thing to go up or down?
I would, in a way, I would expect it to be higher because I think the enzymes attached to they attach to the interface, and they can
Okay.
actually act. Some of them can act as a surfactant. So in a
Okay.
way, the bubbles would be more rigid and would be harder to coalesce. That would be what I would expect.
Okay, and if you now compare the coalescing data with the non-coalescing data, I guess the non-coalescing are higher, so if you strengthen the non-coalescing nature, they should be even higher.
With scale, yeah.
Okay, it's a good argument. I don't think, I have no
But,
idea
I-
what's
I-
gonna happen.
Yeah, that's what I would believe.
I would argue that a certain amount of area is taken up by protein. That fraction of area taken up of the bubbles of the gas-liquid interface taken up by protein does not contribute to the transfer, so it would lower this thing. But I buy your argument that the stiffness of the interface should probably, if anything, increase. But can you tell me what surfactants typically do?
They have that effect of
No, they don't.
keeping the bubbles.
Now, if you take a surfactant and toss that into onto any gas, liquid, gas, solid interface. What's the purpose of a surfactant? Very
I would
generically,
say-
not in your situation. Take your detergent surfactant. Why do you need to add a surfactant?
Let's see where you want to go.
Well, what I'm driving at, it lowers interfacial tension.
Yes.
So if you keep lowering interfacial tension here, what's going to happen with the coalescing effects?
It will be higher.
They would coalesce a lot more.
They will
right? So
coalesce more because they
in
would have,
fact,
yes.
So the surfactant nature of the proteins, if anything, would be expected to drastically lower the KLA. Now, we're talking now 3 effects. We have no idea which way this is going. So that would be an interesting
Yes.
point to study. And this was not meant to check up
No,
on
no,
your knowledge.
I understand what,
only,
yeah,
but,
I understand
because
where
it's
your
really
point
not
is.
clear.
Yeah,
what's-
it's not
what's
clear,
going
but
on.
I think I discussed that it's not clear what is actually the effect.
Yeah.
Because, and an interesting thing that I do see is that when I run my experiments in this reactor and I take the videos, there is a different regime compared with just water or with an enzyme there.
Yeah.
But in a way, we do see more bubbles.
Yeah. Yeah.
So I guess I have 2 questions kind of building off of that. So I like where you're going, Andy. So certainly as you think about, the more surfactant you have, the less you can stabilize really small droplets, right? So you do have, it's harder to get stable droplets that are
Yes.
really small, the more spring. But I guess a question, so we had antifoam almost always, whenever we're doing an oxidation reaction, right? So
Yeah.
if you've ever foamed out a reactor, no matter what scale you've done it at, it is a pretty horrific thing. Can you comment what antifoam might do, what it might be, how it might impact, kind of extending off of that? So surfactant, an antifoam is, some are surfactants, some are the opposite of surfactants. Like,
Yeah.
what role do you think antifoam plays in KLA measurements?
Yeah, so it will definitely have an effect on the area, that's for sure. So the way the bubbles are, and that's it depends on the type of antifoam, because they can actually have the opposite effect of the enzymes. So they can actually increase the surface tension, so in order also to decrease the foaming effect. So in a way, I mean, it's really hard to predict, and I don't know how it will behave. But it's definitely interesting to test, because we do have if we do have an antifoam that will increase the surface tension, and then you have an enzyme that does decrease it, then that would have, in which extent would that affect the bubbles? So it would be interesting to study that, and I think that would be a very interesting follow-up on the work that I've done.
I guess maybe as an extension of that.
Yeah.
So I mean, what you're kind of alluding to is the fact that sometimes you might just have to empirically measure, right? You
Yes.
might have to empirically
Yes.
measure KLA, right?
Yes.
I spend a lot of my time thinking about how to go from 100 milliliters to 10,000 liters.
Yeah.
We can't do KLA tests with true reaction mimics at a 10,000 liter scale, right? So like,
Can or cannot?
can't. We can't afford to.
Can't
Meaning
afford
like, if you're going to throw it out, if you're just going to do a dummy run at the beginning of a campaign and you're just going to throw it out.
Okay.
So I guess a question that I would have is, when your solution that you actually can which you can put into a reactor when you're trying to choose one reactor versus another in a factory, when you can't actually have a perfect mimic for the antifoam, the surfactant, the self-react components, all of the salts that might be there, cofactors, etc., what strategy should you follow?
So I would probably pick to choose the one that is present in higher concentrations. So I would assume that may have a higher effect on the bubbles, and you could go from that. And I mean, in a way, you would know what you want to put into your reactor, right? And you have an idea probably from previous experiments how fast you do transfer oxygen, at least what is your productivity, right? And then based on that value, you could kind of have an idea, okay, my KLA could roughly be this, and then based on that, try to run it in a small scale. I would use other parameters than KLA to mimic it, and not use the KLA as the parameter that would transfer across scales, because it does not. So.
Can we look at your data here again, your calculations here? Could you comment on what scale-up does to your KLA predictability? So the notion is, we are, in biotech, you use KLA because that's the limiting, that characterizes the limiting process. And if you keep KLA constant across different scales, your small scale model will dutifully reflect what you find on large scale. That's the
principle.
The standard mantra that we're all operating under. Look at the KLA data, and could you comment? And could you comment for both columns?
Yeah, so that's what I also trying to point out. I don't believe that mimicking KLA in small scale is the right way to do your experiment.
Mm-hmm.
Because in smaller scale, you will have lower KLA. And so what I believe is that we just have to make sure that the reaction rate is not limited by that factor when you run a reaction at 100 milliliters reactor. Because you do know if that would be your major problem, as soon as you change scale, that could be improved.
Mm-hmm.
So, naturally. So,
Mm-hmm.
in a way, I would believe that I would dose the enzyme in order to have the rate that that reactor can couple with the oxygen transfer, and within that, see if there would be other limitations. So that would be my approach, based on this basis that KLA do increase with scale.
Mm-hmm. Mm-hmm. Could you, two more questions on this one, and one comment. Could you compare the situation that KLA does change, apparently, or at least according to the calculations,
Yes.
Across various scales? Could you compare the two columns and comment on that?
Yeah, so what we can see, like I mentioned, in coalition conditions, we do see a clear increase with KLA in scale, and in non-coalitions, we do see that it's similar, and there's a point where it actually decreases, but it's based on the floating of the reactor.
For which of the columns would you have more stomach ache to take KLA on small scale and scale it up?
The
For
one on the
coalescing or for non-coalescing?
To replicate?
Yes.
No, but based on these results,
Yes.
I mean, it would be definitely harder to do the one on the right, because we cannot reach those numbers.
Harder? Well, I would strongly disagree, because see on the left, you go from 10 liters to 100 cubic meters.
Yes.
You go from 169 to 421. That's what factor of 2.5.
Yes.
On the right, you go from 518, let's pick the one at 10 cubic meters, from 518 to 662, that's what, 15 to 20%. Now, there's a famous dictum in engineering that you do the calculations, then you add 20% to it to sort of be safe, your safety margin. So along those lines, if you had a non-coalescing condition, which by the way I think we do have, so we can almost forget about the data on the left in terms of active use or actual use in the reactor. On the right-hand side, there's a little bit of a trend, but it's not really, first of all, it's not that major, and second of all, it's going in the right direction. If you now look at your small-scale reactor, and of course, this is 10 liters,
Yeah, so it has to be
further calculate that for 1 liter or 100 milliliters or so, but the trend is there. You would essentially assume your KLA is, let's suppose, 518. In reality, on large scale, you would find it 662. That's a way better situation than the other way around, where you are over-optimistic on small scale and then get the disaster on large scale. I'd much rather go to my industry boss and say, hey, I get 518 for SKLA, that's what we're going to be getting on large scale, and voila, the whole thing works even better than anticipated.
Yeah, and
so I don't think that it's
okay, I understand what you're trying to get. Yeah, that's true. Like, yeah, if we could get that number, of course it would be better. But what I'm trying to say is that it's hard for me to believe that in 100 mils you can get that number.
Okay, now.
That's what I'm trying to say. So,
The usefulness of this table,
Yeah.
I think, is in cautioning us against assuming that keeping KLA constant is that easy and
Yes.
actually solves our problems.
I agree.
Yeah.
But I also question it because this is not measured with the presence of an enzyme and all the other
Yeah. Yeah.
compounds,
Yeah, yeah,
that,
yeah.
all the other molecules that
Yeah.
we do have,
Yeah.
and the salts and the
Yeah.
antifoams.
Yes.
And so that we don't know that. That's
Yeah.
not measured. So that's why I question it, and I believe that has to be investigated.
So that directly leads into my last question before I have to make a comment also.
Uh-huh.
Are you aware of any investigation, either for fermentations or for biotransformations, that have checked up on this KLA dependence on various scales?
There are. I don't have. I've read.
Do you
some
remember
that is-
names or what situations, what regime they covered?
I don't have them on top of my mind, but I know there were studies, and quite a lot of studies, especially on fermentations.
Okay, I'm not familiar with that area, so this is a question I didn't know the answer to. What I do remember is that Boyster-Botz in Munich and Büchs in Aachen, for instance, both have investigated the KLA dependence in a 96 or 384 well plate compared to a couple of milliliters. So they have looked at a regime that's way smaller than
Very
this
small,
one,
yeah.
and have concluded that this is not an easy game.
Yeah,
So
not
there is at least a
familiar
bit, and you say there's studies on fermentations. So there is some empirical evidence beyond just the calculations that should give us at least some idea of in how much danger we're in when we take KLA and then go on different scales.
Yes.
The one comment here, you write, third row, below the table. The proteins are surface active and can reduce bubbles coalescence. In light of the fact that you claim that they're surface active, then they actually should not reduce bubbles coalescence. So you might want to change that in the final version. One of the very few spots where I would suggest.
Yeah, no, that's right, but
The way it's written, it's 90% wrong.
yeah.
But
Not
it's
so much
easy to
money,
fix
but-
and there's no other
But
consequence.
the thing, no,
You don't want to have anything on record that can be proved wrong later.
So before we move
But-
away,
yeah, no, go ahead. You can calm down. No, it's fine.
you want to keep up? Before we move away from this table, I liked Eddie's very first question as to do you believe this table? Because I looked at this table and was like, what is happening? Because for me, a 100 milliliter reactor, I can probably get to, so I do mine in different units because I come from the small molecule space, somewhere around 250 is probably, inverse hours is probably about the highest that I think we could reasonably get to in the automated reactors we use. At a 100 liter scale, we're at about 50. At a 10,000 liter scale, we might be around 5. This just goes to show you how terrible these reactors are for, for doing these types of reactions, right? I guess in that, one of the things that I spend a lot of time thinking about is if you're presented with a reactor of 5, for me, a lot of the question is if I were redesigning that reactor, if I needed to call up someone and do something different to that reactor, if I needed to think about a different reactor format, can you think about, or can you comment on reactor design decisions that might drive to a different regime than what you might be presented with when you walk up to a reactor that might be 5, for example?
So I would look at, if I would have total freedom, I would look at the impeller. Definitely, I would look at the position of the impeller in the reactor. I would also look at the baffles in the reactor and the sparger itself. So, and the position of the sparger. So all of those are important to make this regime.
Yeah, so again, not working in bioreactors, I don't have a sparger in most cases.
You just
What
have
does a
to
good
choose.
sparger look like? Yeah, no, we
Yeah.
do. I mean, it's pretty terrible. But what is a good
Give the
sparger?
simple answer, tell them to buy one.
mean, I would place it right below my impeller, and probably a ring could do the job. There are more fancy impellers, but where you could like easily spark your gas from the bottom, and it would be dispersed with your turbines. So I would say that also the positioning is really important to get those readings. Yeah.
It's me now.
I have one more thing before 4 o'clock that I need to discuss. So I'm completely fine to move on.
Okay, sure.
There.
Yeah. I think this is the question that we were discussing before as well. When you talk about one of the reasons when you increase the steering rate, there is a reactivation of the engine, right? So you know which other variable actually can you change to prove this? That there is that you can increase actually the molecular collision by increasing the steering rate.
So instead of changing my steering,
Yeah.
but without steering, or I would need the steering.
Yeah,
I would
yeah.
say.
You can have the steering if you want to.
Okay, so if I wouldn't correlate it with the power per volume, what
Exactly.
would I use
Yeah.
it?
And another one that you can use to prove this hypothesis. Yeah. There are only two possibilities.
I mean,
So,
you
yeah.
can use our RPMs, but the steering speed, that correlates with the power per volume, and I don't believe that's the right way to go.
Okay. So we are like 20 people in this room, right?
Yeah.
Okay. So imagine that we switch off actually the lights. Okay? And we start to walk. And we collide, right?
Yes.
So, and you want to prove actually that the collision is the reason actually. So what can you do to increase the number of collisions here?
Put more people.
Exactly.
So
Yes.
yeah, I would change the enzyme concentration. That's also something.
Have you thought of that?
Yeah, definitely, yes.
He's a great
Definitely, definitely.
Okay, but you haven't done any experiment on that, right?
No, so yeah, I wanted to do that. It was definitely on my plans, but one of the reasons why I didn't do it was because I didn't have enough enzyme. So I do not produce my own enzymes. They are supplied by different partners. So I did not have enough in order to do enough experiments to do that. And then the other problem also that was observed is that as you increase the enzyme concentration, you can foam much more. So,
Yeah.
and I don't want to add anti-foam intentionally. And so for all those like small details, I didn't do it, but I do believe it can be done.
You could write into your publication, Mark does it too.
So you said there are only 2 ways to do it. What's the other way?
Oh,
There is
okay.
another way.
I can think of 3 ways. But,
So changing the concentration of enzyme and besides the steering, what else would I do?
I don't know.
That's the 2-way, no?
well, I mean, so taking his exact same example, like what if the room were
You can also
smaller?
remove people.
Like,
Yeah,
no, like what if
definitely.
the room? No, what if the room were smaller?
Yeah, okay,
Right.
sure.
So obviously
Yeah.
you could get to
Change
the
the
same
size.
power per unit volume in a much smaller reactor,
Yes.
and now you're going to be improving the frequency,
frequency.
mostly kind of protein wall collisions.
Yes.
Yep.
Yeah,
Yep.
that's
Yeah.
also,
Yeah. And the third one, again, I spent,
yeah.
again, going back to my very first comment, I don't do a lot of work with RDTs, but I do a lot of work with a lot of variety of impellers.
Mm-hmm.
So the other thing that is maybe a little more subtle is you could actually change the specific impeller. You can keep exactly the same power per unit volume,
Mhm.
but you're going to be dramatically changing the collision
Definitely.
frequency. Yep.
Mhm.
And that all ties, and that in a lot of ways ties back to, ties back to, turbulent
Yeah.
and dissipation rate, things like that, right? So those are all.
Yeah, I do
Yep.
agree.
Yep.
Yeah, that's true. That's something, it would be really interesting to do.
I have a comment, a small comment actually. Let's go to page 33, to the table 3.1, just to put an example. Here you are talking about the half-life and increasing power inputs. There is an increase, then there is a decrease. that is a little bit difficult to explain, right? You explain that on the text. And you know, it happens several times in the text that you know you have these kind of increases, decreases that you cannot explain. They are not easy to explain, right? Especially when the difference in the numbers are not so high.
Yes.
But you know, in the text, you still say there is an increase and there is a decrease, you know, and in some cases, if you consider the standard deviation that you have here, in this case is the 8%, is 3.1.
3.1.
Sorry.
It's on page 33. Previous one, no? Yeah, it's just an example, this table,
Yes,
you know?
yes, yes.
If you look at the half-life, you know, there is an increase, a slight increase actually from 1.5 to 2.
Yeah.
Then there is a decrease. And you know, this is just an example because in many places, well, in several places actually in the text, you say there is an increase, there is a decrease. And you know, for instance, in this case, that the standard deviation, let's say, is a little bit higher than in the other cases. You know, what I recommend you actually for the future is actually you can do an ANOVA test. You know, one-way ANOVA. It takes 2 minutes. It's very quick and easy. And then you don't have to say that there is an increase or there is a decrease, because there is not, probably in this case, you know. So it's very healthy actually. I always recommend the students to do this ANOVA because it takes nothing and it's much easier actually afterwards to interpret the results.
Yes, thank you.
I first recommend replication. Then,
yeah, but in this case, she has replication actually.
Yeah. And one comment here, what's missing is the power input at 0 watt per liter.
Yes. Yes, it is missing.
Jane, you will go, or can I start?
you can start. I have. You can go ahead. It's going to take a second.
Well, we got 50 minutes. That's a nice little chunk of time here. I want to go down the path. You sort of seem to imply that collisions lead to inactivation. I take the opposite view and say collisions are collisions. Why on earth should they lead to deactivation? You probably will answer me that Chaussette with lysozyme showed that. I come back and say, wait a minute, lysozyme is a proteolytic type enzyme, and you can argue that collisions mean that there is a cleavage in the main chain of the other protein, the other protein molecule. But NOXes colliding don't act proteolytically. So why should collisions lead to inactivations here?
So what I suggest is that it will affect its structure. So it would change, it would destabilize it. And what I believe is that the hydrophobic residues would be exposed. And so therefore, these proteins would aggregate and became larger aggregates. And the collisions of native proteins with that hydrophobic surface would enhance the deactivation of the native protein. So that's the way I can explain it. And that's why I believe these collisions enhance that mechanism, if you can call it mechanism.
I think that's a good line to follow. So that you ultimately have sticky collisions, right? In physical chemistry sense, which we would call aggregation in biotech. Wouldn't that be a second order process? Because you need two molecules to collide. That's a classical situation for a second order process. But you find, I think correctly, that this is the first order process.
Yeah, but so what I would say is that just putting a protein in solution with time, it would deactivate. So that could also start the mechanism. So and then it would be enhanced with the other effect.
Okay, Yeah, that's a good argument, even if you do nothing, right? You
even if
still
you do
have,
nothing, yeah.
quiescent, everything.
If you keep
right?
the throating, it will lose its activity over time. So
Mhm.
we do see
Mhm.
by the quiescent experiments that time has an effect.
Yeah.
So just having a protein
Yeah.
solubilized, standing in the bench,
Yeah.
it will deactivate
Yeah.
with time.
Yeah, it will.
It may take weeks, but it can
Yeah.
also take a day.
Yes,
So, and
Yes.
that mechanism
yes,
would end, would
Yes.
start
yes.
with the starting point for that.
Yes. So I think it's very useful to think of this not just as a second order process of two active enzymes, two active molecules colliding and sticking, and then they turning inactive through the sticking process, but essentially having this notion that you have a population that is not active, and I don't want to imply with my hand movement they're unfolded, because that's a very
Yes.
separate issue, right? But that you have something inactive,
Mm-hmm.
and that you then hit an active molecule that sometimes sticks, sometimes also gets inactive, whatever we then propose.
Mm-hmm.
What we are effectively discussing here is the opening to a mechanistic model. And I think what sort of a nice next step from you after your data would be to actually propose a mechanistic model, ideally one that's testable, and then say, okay, how do we now fit the data with an even crude mechanistic model? Because I could just take your own slide where you say scale down philosophy, and then number 3, you very correctly point out that ultimately everything has to run through a mechanistic model. There's no one in your thesis yet. No, I'm not suggesting you should put one in, but so for
How
next
to follow
steps,
up.
I think you do mention it at one point in passing. I think this is very important and shouldn't just be mentioned sort of as a byproduct, is to, after your initial data set that kind of clarifies a lot, the next thing, or one of the next steps should be to come up with a simple mechanistic model, but one that's testable, of course, otherwise it's just sort of an academic exercise, because that will then help us figure out countermeasures, right? If aggregation of any kind is important, then increasing the enzyme concentration is very detrimental. So you need to figure out a way how not to do that. If the hydrophobic issue is most important, then we need to figure out a way to reduce hydrophobicity, which could be done via protein engineering or via other measures, including mobilization. If you use the hydrophobic part of your enzyme and to cover that up via immobilization, then in theory you should just have the hydrophilic part sticking out, which should not deactivate as quickly.
Yes.
So,
That's good suggestions.
and while I'm on this, so you got flack from Shane for writing down scale down philosophy. You could bypass that, because if you replace your word scale down philosophy just by process development philosophy, this becomes more or less scale independent. If he says, I don't care whether I use a 10,000 liter reactor, we have plenty of those, so why not use them? And if the cost argument is moot in industry, which it mostly is, then it's still valid to go via mechanistic model, and it's still useful to understand what's actually killing his enzyme. Right? So it's not just the scale down part that's important, although for academics, of course, that boils down to it, because we cannot go into even 10 liter reactors. It would kill us on the cost front.
Yeah, and just kind of building on that. So you made a comment before that in low margin industries, 210 hours half-life is pretty atrocious. I mean, for me, we're usually trying to get from a 10-hour to a 20-hour half-life, right? Like that is actually super influential, right? So the ability, because we do regularly have 5 and 10-hour half-lives for some of our enzymes, right? So, so a lot of what we do is how do you kind of squeeze out every last bit of stability out of a particular enzyme. So it's an interesting.
I'm glad to hear that, because that means that her numbers already put them into scoring range for you guys.
I mean, we have not yet commercialized, but have run at commercial scale on our enzyme. So I'll say it that way. So you can run NOxes at scale. So at a scale that's very important and very relevant to us. You can do it. We have demonstrated you can do it. But they're not active for very long.
No.
I think proline hydroxylase is another class of compounds where you could say exactly the same thing. They're not active for very long, but usually they're sufficiently active or sufficiently stable. I want to go back to a question or a comment that you made. You kind of, your hand gesture was, when you start talking about unfolding, this discussion, this is a totally separate discussion. I actually think it's a really important discussion though. Can you comment? I mean, I don't know if this is more for Andy or for Mafalda. What?
Fortunately, I sit here.
So can you speculate what happens when protein starts unfolding?
Yeah, so when first they lose their activity, right, and then they just unfold and they aggregate, and so that's what we know. Then if I couldn't measure that. I mean, of course it would be. That's why it would be interesting to measure that somehow. I'm not an expert on that field, but that would be really interesting to see because that can happen, right? This destabilization can be due to the unfolding of the protein, and then it's just like its active site is not active anymore, and then the enzyme doesn't have sufficient activity. So I think it's definitely a very important characteristics of the enzyme that has to be looked into. But I also believe it's really hard to do it. It's not that simple.
Can you speculate how you might?
First I would need to use purified proteins. That's the first thing I would go for because I cannot.
What if it's not your protein? But what if it's not your enzyme that's denaturing?
Yeah, then you would immediately see that. So if you would purify a protein and then you would see, okay, it's not the enzyme, then you'd say, okay, maybe there's something in this cell-free extract, any compound that we may need to remove because it's destabilizing the protein. That would be a nice call, actually. And I think, there was also a way that I've shown that on my thesis where I tested 2 different NOxes that have been exposed to different cell lysis methods. Yeah. So one used detergent and the other did not. And it was clear to see that the one that used detergent, they were less active. So that was actually having a negative effect on the activity and furthermore on the stability. So that could be a way.
Comment, an excellent question. When you were at Georgia Tech, I'm sure that we in group meeting discussed what we in group call the nanotempered data. So that was essentially the differential scanning fluorimetry via sort of the protein's own fluorescence, self-fluorescence of tyrosine and tryptophan residues. What that ends up effectively doing for you is very unexpected because you can sort of at least give a good estimate of the amount of folded versus unfolded protein. As long as you sample and immediately go onto this instrument, it's going to take you 3 minutes per measurement, so it's really not a long thing. But there are actually methods coming up that will give you at least a rough answer as to how much of your protein is still folded, which is what you really care about, versus how much is sort of already down the toilet in whatever shape or form.
Yeah, and then
nano DFC. This is what we would have said. Nano DFC, so nano, calorimetry.
Yeah.
Different price point.
Yeah.
Very effective.
Yeah. Those are the methods that I would think about. Is scanning, any type of, thermal stability measurement.
Yeah, definitely.
Is probably the most direct way to actually answer that.
Yeah, that could be.
I was going to ask a similar question, maybe, likely on methods that you've never used. But, you talk in the thesis about exposure of hydrophobic residues to, let's just say, surfaces.
Yes.
So first, a comment, so the 90% wrong comment that I saw was you call the glass surface hydrophobic. A contact angle of glass is something like 40, right? It's a pretty hydrophilic surface. No, that's not to say it's not destabilizing, but it's probably not hydrophobic. So you might want to correct But maybe kind of in the same portion of the thesis, I don't remember exactly what page number, you also make a comment that, and I think you actually had it in your future directions, you know, thinking about what happens when you expose a protein to an air-liquid interface. Are you aware of any experimental techniques that would help you to quantify how much protein is at the surface and what its orientation might be, whether or not it's destabilizing, stabilizing, etc. Any thoughts there?
On the method itself,
Yeah.
I don't know.
I mean, this is pretty far from where you work. But.
I don't know the method.
So
that comes to the top of my head.
Yeah. So the one so you do make a comment in your surface tension is one.
Yeah.
But there are some techniques like Langmuir films, like a Langmuir Blodgett-Trough, for example, is probably a device, again, probably may or may not have access to, but that's a device that it would actually tell you an awful lot about how your protein reorients on the surface. You can measure surface pressures and things like that with that. And that would tell you an awful lot about how your protein stabilizes bubbles, for example, but also how much you unfold a protein and how much you can refold that protein as you change the dynamics of that. It would be an interesting thing to think about because in your future directions you had, boy, I'd like to understand how hydrophobic surfaces present themselves. That's one way you could consider. Like I said, that wasn't a question because I would have been really surprised.
Yeah, no. I mean, I agree, and that's something that I would also like to learn more because I believe that the continuation of my work would have to go more deep into these techniques. And so now, after having the whole conditions, big tank, all the mess, then we need to go to the small, tiny detail, purify protein, and test everything that's possible. So I do agree with that.
That would be particularly useful if you actually could compare different NOxes. Because to take a single NOx and say, here's my sort of set of data on any sort of specific technique, that could be surface plasmon resonance or any of that stuff that sort of somehow characterizes the interaction of hydrophobic part of a protein with an interface, gives you a data point.
Yeah.
Well, so what, right? If you get 10 NOxes, you already can sort of get a feel for how a protein should look like, that at least gives you better performance than another. And so you can do the 10 to 20 with that type of technique. You can probably, or maybe you can do the 10 to 100, you will not do the 10 to 1,000. But if 10 to 20 is already some sort of what would be useful, then that's certainly something that is within the realm of doability.
I mean, in the protein engineering world, like SBR on 96-hole plate is out there. It's probably not a super common piece of equipment. No. It's not to say that it can't be done. No. But yes, for some of those techniques you would need collaborators because this is not something is available.
Definitely.
These are not super common.
No, not around.
So you had a comment, I think it was slide 44, maybe it was one of your future direction slides. It was pretty late.
Okay.
Maybe it wasn't that late. It was pretty late, I guess, like 40, I think it was 44. Yeah, 44. In that one. You make a comment, geometric similarity may not be mandated.
Yeah.
Can you explain? Can you expand? Because this is very important to me, and I want to understand whether or not you agree or disagree with my perspective. I think that's the question.
Yes, so like I was saying, what I claim to be the most important thing to mimic is the rate limiting step. So, for instance, if it is, I don't know, your oxygen transfer rate, like I was saying, or more, let's talk about stability. If we do want to reach these high interfacial areas, that may not mean that you would design a reactor exactly the same way that would be in large scale, because that's the effect you want to study. And that's why I say that you may not maintain this geometrical similarity, because in order to reach that high interfacial areas in the small scale comparable to a large scale, you would probably need other impellers that maybe you don't even have in large scale, but they can do the job at small scale to mimic that condition. So that's why I claim that they may not be the case. So it can also be maintained, but there are cases that they may not. So, and that's the basis for my comment.
So
Yeah.
wholeheartedly agree with that.
Yeah.
So while we're on this, I strongly agree with 1 and 3. I don't really agree with 2.
Okay.
If you do your large-scale experiment in a lemon-shaped reactor and then move to sort of some circular loop reactor on large scale, why not? As long as you either, or no, both, have a mathematical model of what happens and keep the rate-limiting processes constant, or know what your rate-limiting process is at various scales. Who cares about similar environment?
Yeah, okay, when I say similar environment, it's maintaining that rate-limiting step. And for that, that's what I mean with that.
Okay, fair enough, yes. But so
it's the environment that creates that rate-limiting step.
Yes, so I would phrase number 2 more strongly and say, who cares about geometric similarity? Now, if you happen to have reactors that are geometrically similar, well, hey, fine. But I think among the 3 statements, 1 and 3 are absolutely crucial, whereas 2 is sort of, if I phrased it in a hard way, which I don't want to, it sounds too wishy-washy, kind of. 1 and 3 is really what drives the guidelines here. Right, and you took them from Norman, I don't know, but
I mean, they are based on.
Okay. No, I
That's,
think
I mean, he proposes this, he talks a lot about this philosophy, how you do the fermentation reactions.
Right.
When they are scaled down, they are only based on your empirical knowledge. So, and these are the kind of the suggestions that he claims are the steps to scale down.
So 2 I think is kind of nice, whereas 1 and 3 is really the heat, the heart of the matter, the meat of all of this.
Yeah.
Yeah.
But can do.
And while you're on 44, can we go to 46? Now I understand this is not quantitative. No problem. I buy your oxygen limitation line. I don't necessarily buy some of the other lines. I might buy the cost lines, by the way. Yeah, if you go too high, it's not feasible. Define inadequate mixing for me.
It's the one where you cannot ensure sufficient oxygen transfer rate. So if you do need to have high oxygen transfer rate, you do need to steer enough. So it may be needed, like you may find, okay, your enzyme, it's destabilized by steering, right? So it would be nice to have a low steering speed, but in order to reach this productivity, you need to...
But isn't that also captured by the oxygen limitation issue? So if you just left out the inadequate mixing, I'm just asking a question, I'm not saying this is what happens here. If you just left out the inadequate mixing, yes, the oxygen limitation line would creep to higher and higher gas supply points. No question about that.
Yes.
But do we really need to worry about inadequate mixing in a situation where if you ran mixing time studies, and I learned from an industry speaker, there's a Bourne reaction. You probably know the Bourne protocol, this guy who shoots everybody up and then vanishes. I think it's called the Bourne protocols. There's a Bourne reaction where you can map out mixing time scales, and the chemical reaction is really nice. And my suspicion is that this inadequate mixing line will be so close to the ordinate. In other words, your mechanical stirring would have to be so low to really be inadequate that you can almost forget about that line in our context. the gas-liquid interface damage, that's an interesting one. So you imply with your putting it in here that to lower gas-liquid interfacial damage, I should stir the heck out of things because my line sort of decreases with increasing stirring. Is that really true?
No, this defines the half-life. So the half-life will be lower as I stir more.
Ooh, so you already mechanistically interpret your findings.
No, but when I proposed it, was thinking about how the half-life of an enzyme will change due to these conditions.
Yes.
So that's why I assume when I do stir more, I will have a higher interfacial area, and that will decrease my half-life of the enzyme.
So at
That's
this, yes, at the,
How I
you also imply that at the same gas supply, if you limit your mechanical stirring, you could move from being outside the operating window towards an point inside the operating window. I guess, yes, your data do show that. Although the interfacial, the presence of interfacial area is so important that just lowering mechanical stirring might not be the right way to do it. So that line, I'd say, is something that would be crucially important for this discussion here.
Yeah.
I also find it interesting way to put your collision lines in there. Quick thoughts. So mechanical stirring increases collisions. You think that collisions are bad, so that's why there's a negative slope. Yes. Okay.
Yes.
And I guess you do not want to imply that the collision line necessarily limits your operating window because so this might be outside or to the right of the intersection between gas-liquid interfacial damage and cost.
Yeah.
Yeah. Okay. Interesting way. I mean, this is a great way to think about it. Your advisor knows I'm very fond of these plots of his because he's the only one in the world thinking about it. And it's which is great that he thinks about it, right? It's a trophy, so he's the only one, but can't blame him for that. Ultimately, it is the right way of thinking. What's the operating window here? So I'm still trying to wrap my head around this, whether this should be qualitatively really the way to think. And my next question would be, that's a bit speculative, if you were in the operating window, where would you want to be if you just had performance in mind? Forget the cost for a second.
Okay. I mean, I would place myself where I would get higher oxygen transfer. I mean, depends on what I want to. I mean, depends on my productivity, right? Because that would determine my choice.
Okay, but could you speculate where you would find the highest productivity in this thing? With the Noxus as an example.
Yes.
Where anything happens and they die, right? That's a pretty bad situation.
Yeah, I mean, if we would assume that this is the operational window of my Nox,
yes,
I would try to be like, and assuming that, inside that green window, I would probably steer more and supply it. So like more on the right hand.
Yep.
Like on the bottom corner.
So in other words, the mechanical stirring would have to be there.
Yeah.
Yeah.
I would assume that.
Yeah.
Yeah. And also depends like how much oxygen can you actually put, right? And so if you can only have 8% of oxygen in your feed gas, then you would have to steer.
I think it would be an easy argument to make that, let's suppose we project 20 years out. Now that's hard for you because your scientific time scale is 3 to 5 years at this point. To say, what's going to happen in 20 years is kind of asking us what's going to happen in 200 years. So, but I guess what you're saying is, and correct me if I'm wrong, is that further research should move the gas-liquid interface damage line upwards. That's good. But the oxygen limitation line could be the hardest thing to overcome. And so if you wanted to get productivity up, I mean, productivity now sort of just total turnover of your enzyme. The more it does before it dies, the better, right? So you could do that with a highly active enzyme at short time. You could do it with a less active enzyme over a long time. If you just take total turnover number as the productivity criterion, which I'll argue tomorrow morning is the way to go, by the way, but then I guess the oxygen limitation is probably something that is hardest to overcome and least accessible to the type of research you're doing, which should suggest that the gas-liquid damage line is what we need to work on.
Yeah. Yes, I mean, I kind of say that because also the oxygen limitations are very dependent on the equipment and on the way that is done. And if we want biocatalysis to move fast and bioxidations to go fast, we need to use what is currently there. And so,
in terms of equipment.
yes, in terms of equipment.
Yeah, I agree.
So if we do want that,
you never build stuff just for this.
exactly. And so, in a way, changing, that's where the changes on the improving the stability of these enzymes towards this condition could actually have that process improvement that we aim for. So I would focus on that, at least currently. Maybe someday there will be a much better reactor, right? But chemical industry is quite old.
And I would agree with that. And if you then also point out that the operating window is not everything is equally green, you want to probably be in the right-hand side of this thing, then my comment on inadequate mixing is effectively not very important because you don't want to be on that side anyway, or you can't be on that side anyway because the oxygen limitation is taking away too much of your potential operating space. So it's more useful to think about the part further to the right.
Yeah.
I guess I have two comments more than questions kind of following up on this. I think one of the things, so I would have answered that question totally differently, and that's not a critique, but it's because I sit in a very different space. For me, I operate as far as I can from whichever line is fuzziest. And what I mean by that is the one that you're least certain about, right? So if it turns out that you don't actually have any concept of how susceptible you are to gas-liquid interface damage, the most robust process is one where you know the most about. This goes back to your comment about ANOVA analysis earlier. So there are mathematical tools that you can use to help you understand when you draw that line, not just what its shape is, what its slope is, but also how certain you are about that. And you might find there is a part of that operating window which is a heck of a lot easier to reproducibly and reliably deliver on, that might not be in one of those four corners. It might be smack in the middle, or it might be all the way at the bottom. That's one comment. Again, I don't fault you for not having that perspective. It's not a subtlety to me, right? It's something that is actually learned the hard way over many, many years. So. The other piece, I'm a little surprised. I can probably name one person in the entire world that has ever even postulated the idea of improving KM through protein engineering. Sitting over there. So the one retort to Annie's comment is the oxygen limitation is not just the kinetics of oxygen transfer, right?
So no, that's true.
Obviously, your
enzyme, the
introduction talks about that.
I would actually agree with
talk
that.
about that.
Yes.
That's true.
Yes, I'll actually agree with that.
I'm glad you mentioned it. Yes.
Yeah. Or phrasing it a different way, if you already have an OTR, an oxygen transfer rate limitation, that is a hard limit. Your OUR should definitely not be limited by the binding constant.
Yes.
That would sort of go further down from the Vmax. Yes, I think that's a very good point.
on, guys, yeah. We can finish before time, it's not a problem.
If I was Monty Python, I would now ask you who won the cup final in 1952.
So, are we done?
I'm finished. I think I'm finished.
As nobody else wants to question the candidate, this concludes the questioning session and also the public part of the defense. What happens now is that the assessment committee convene and write a recommendation for award of the PhD degree and forward their recommendation to the PhD program committee. If the recommendation is positive, rector and the dean of research will issue a diploma to Mafalda stating that she has been awarded a PhD degree from the degree. With these words, I declare the defense proceedings to be concluded. I would like to say that the reception will be at the building 229 in room 003. So thank you all for coming. Thank you. Okay, apparently it has changed. The room is 049 instead of 049.
I think
Oh, okay.
it was the reception.
Okay, then I will not 4 o'clock.
Do you have anything last to say to your 3 fans who are watching? All right, stream's over, guys. 3 hours, 12 minutes. Eesh.
Sure you were.